So I hope all team members, participants have joined this day two pre-webinar session. So shall we start, ma'am?
Yes, Prince.
Yeah.
Shall we get started?
Yes, ma'am. So hi, good morning, everyone. So from Chipin team, myself, Prince Hani. On behalf of Chipin team, I welcome you all to this day two of 3-day pre-event webinar session on digital design flow by Coral team as a part of Digital Design Hackathon 2025, hosted by Chipin Center, CDEC, Bangalore. So first of all, I would like to thanks again Coral team for accepting our invitation for conducting this pre-event webinar sessions. And this webinar session will provide essential guidance for upcoming Digital Design Hackathon 2025 starting from 15th of this month. So from Coral team, today we have Asha Patil ma'am joined online. She will be the speaker for today's webinar. On behalf of Chipin team, I warmly welcome you, ma'am, today's webinar.
Thank you.
So now I would like to request you, ma'am, to take over the session and brief the participants. Thank you, ma'am.
Yes. Thank you, Prince. Thanks for giving a welcome note. And I welcome everyone here who are going to take up a hackathon. I wish you all the best also for your hackathon session. So this particular session will be as a prerequisites that you require before you start up with any of the problem statement that is given in a hackathon. That will be the prerequisite. So I wish you all the best for that. So let me start with the session. I'll try to give as much as input as much as possible today. uh, Take it as an input straight away, because to begin with any of the uh, board, or before using any of the board demonstration, you should be aware about its specification. You should be aware about the architecture. Then it becomes very easy for you to go ahead with the um, specifications or any of the problem statement. So that was the idea behind conducting this 3 days online session of prerequisite that is required for the hackathon. And I hope you will make use of completely this theoretical session, and as well as a few lab demonstration that we are going to provide you. This will be helpful for you to go ahead with the problem statement and carry out any of the project. So I wish you all the best. So today's agenda will be, I'll be introducing you to the embedded system design, that is Zinc architecture, SOC architecture, a brief overview of that, and we'll be taking you through some lab demonstration, initial lab demonstration that is required, as well as the tool flow that is required. So yesterday's session, FPGA was included, and you would have been introduced to Vivado tool flow and a IP integrator. Today I will introduce you to how to come up with a FPGA embedded system design using FPGA and microprocessor. Okay. And I will be talking about the environment of the integrated development environment of Vivado and Vitis. I will show you from where you can get the address without even having memorizing the things like addresses or all those things. Okay, you can get some driver details, you can get some code reference, that and all I'll be showing. But before getting into a tool, I will talk about the theoretical aspect about the Zinc architecture. This is a huge thing, but I'll try to cover as much as possible. I'll try to give you a hint how much ever it is required for you to go ahead with this hackathon. Okay. So once again, I welcome you all from the Coral Technologies. Okay. So basically, we are all aware that you will be provided with this particular board, pink Z1 or Z2 board, right? So this pink board has a chip, okay, that you can see. It is based on Zinc 7000 SoC. Okay, this is based on Zinc 7000. You can clearly see here a picture of a chip that is placed here, whether it is pink Z1 or Z2 board. It includes XC7Z0201CL G400C, that is the logic chip that is provided. Okay, what this has, this chip has around millions of programmable gates. Okay, so this will allow you to implement some custom hardware accelerator and interfaces. Okay, now there are many other things that are included in this particular chip. No, it is called as a SoC. Okay, SoC. Now this pink board is designed to integrate with Python plus Zinc framework. Okay, that means this provides an environment for programming the board using Python, and also it uses the capability of FPGA for accelerated computing. Okay, and also it makes use of the processor for a for taking up a task of complicated decision making. Okay, so such kind of high performance is possible using this pink board. Before getting into a specification about this pink board, okay, this board has some important features, like it enables hardware software co-design. Okay, because of that it is also called as a embedded system. So we all understand, right? Embedded system design means it is embedded system design means it has capability of solving hardware and a software program. That means you have a hardware that is designed, you will be writing a software code to make this hardware work, and that is what is called as a embedded system design, right? So your Zinc devices will help us to simplify this embedded process design. Whenever we think about embedded system, they are complex. Okay, they have hardware, they have software portion. Okay, both are integrated and projected as a embedded system environment. You are merging these two design, correct? These two component of a software and a hardware, which will help you to create one functionality. Okay, along with that functionality, you can go on doing additional or making additional manipulation or challenges. That is what you are supposed to do in a hackathon also. Zinc system on chip, SoC. I have been telling you SoC. What is SoC? SoC is system on chip. System on chip means it provides you the solution which reduces the complexity. It has ARM Cortex A9. Okay, ARM Cortex A9 processor, and it is dual core. Dual means two similar Cortex A9 processor will be there, along with programmable logic, and it is 7 series fabric along with programmable logic. And these two are there, the blend of these two technologies onto a single SoC. This is the importance of SoC, and it is also called as AP-SoC. Okay, so we have a Zinc family, system on chip family, which integrates software programmability. Software programmability is done by ARM Cortex A9 processor, and hardware programmability. Hardware programmability is carried out by FPGA, enabling you to come up with a hardware acceleration while integrating CPU, DSP, and other peripherals with having a mixed signal functionality onto a single device, and that is called as system on chip. Okay, and your Zinc 7000, which is available as a chip on your pink board, has, or it is equipped with, dual ARM Cortex A9 processor and also it is integrated with Artix 7 or Kintex 7 based on 28 nanometer technology. Okay, Artix 7 and or Kintex 7 based on 7 nanometer technology, programmable logic. It provides a excellent performance for maximum design flow and also for achieving a low power. Okay, so what we do is, okay, why we need zinc? We need zinc for carrying out various functionalities. Okay, carrying out various, you can accomplish hardware system development, you can accomplish software system development, you can come up with a real-time operations, you can come up with a many digital image processing, video processing. Okay, any kind of application. It is used in telecommunication, it is used in robotics, it is used in multiple things. So the applications are vast using this particular SoC design. Now, why they thought of having choosing FPGA and CPU both on single chip? We could have used it separate, right? FPGA technology we have and a microprocessor technology. So it has its own advantage. We all understand that FPGA is good at parallel processing, okay, and your microprocessor is good at at solving an analytical strong analytical logics, and also a flow control mechanism is required. You can go with microprocessor. You want high power, high speed, you can go with FPGA. So having a blend of these two technologies, you can have a data flow from FPGA to your microprocessor or microprocessor to FPGA. Okay, so data will be processed from FPGA to CPU, CPU to FPGA. Independently also, you can work with this FPGA. Independently also, you can work with this microprocessor. Okay, you can also work independently with this FPGA. You can do independently a hardware processing, you can do independently a software processing also. That is also possible. So your Zinc 7000 family has, I told you, it has microprocessor and it has, one second, it has microprocessor and it has FPGA. The one that is highlighted in yellow here, this is called as programmable logic, and here it is FPGA. So we call it as the another name or thing that usually the terminology that we use is programmable logic. And here this is a processing system, okay, which is having, you can see here, no, Cortex A9 MP Core 1, Cortex A9 MP Core 2. Because you have two variants, it is called as a dual. Some of the variants of Zinc Zinc family can have single processor. Okay, some of the family higher end, that is a next logical step, can have quad core processor also. That is 4 cores also is possible. So maximum up to 4 cores you have. Okay, so this is all the thing that you have. This is your CPU. We generally we call it as a CPU 0, CPU 1. Okay, 2 CPUs you have, 2 PS we have. So processing system. So ultimately what we are trying to do is we are trying to explore this. What is connected where? And can I use the one resource that is connected or available on the PS side? Can I use it on PL side? Okay, to perform a data transfer. Because of say suppose I want to I want to have a huge data transfer, continuous video streaming, and that has to happen very fast. Maybe your processing system may fail at one particular point of time. Then that data that is saved here, I wanted to forward it to PL. Okay, I want to store it in a PL side. So you want to process a data, you want to store it on PL side. And you have already some data that is available on PL, you want to process it on PS side. So both are possible. Okay, both are possible. My voice is clear, right? Am I clear?
Yes, yes, ma'am. You are clear, ma'am. Your voice is audible.
Okay. In case you have any doubt, difficulty, please interrupt. Okay. You can. I cannot keep checking on a chat window.
Yeah, yeah,
I
yes,
have.
ma'am.
Yeah.
I
Please
request all
interrupt and.
participants, yeah, ma'am. I request all participants, they can unmute themselves if they have any
Ha,
doubts in between. They can interrupt, no problem. Yeah.
yes. Yes. Please. Okay. You can interrupt and you can talk to me. So we have a dual processor. Now, what all this? What are the features of these? Okay. So that we are going to see now. Whenever you think of any microprocessor, microcontroller, okay, or FPGA, you should know what are the resources that are available so that you can use it for your uh, project or any of the tasks that you want to resolve. Uh, so one thing we understand when we talk about microprocessor is it is a CPU. It will have its own register. It has caches. Okay, cache memory. So on a similar grounds, this also has a cache memory. Now ARM processor it has. Okay, ARM processor. It is 32-bit. Okay, ARM processor it has. So when I talk about Cortex processor, you will get to see Cortex A9. A means application. This kind of CPUs, they are majorly used for application, performing any kind of application. Some variants will have Cortex R processor. R means real time. M means some simple embedded controller based application. So when you think about this block diagram, what is there inside Zinc and how I can make use of this Zinc? So this ARM processor has L1 cache. L1 cache is here only it is mentioned 32 or okay 32 kilobyte 232 is specified here. 32 instruction cache, 32 data cache, 32 bytes, 32 kilobytes of instruction cache and 32 kilobytes. Whenever capital B is mentioned, it is bytes, small b bit. Okay, that you should be very familiar. Similarly, independently, you have another cache here, 32 kilobyte of instruction, 32 kilobyte of data cache. Then you have L2 cache. You can see only one L2 cache here, which is shared between these two. So both the CPUs have one common L2 cache. Okay. L1 cache is called as primary cache. L2 cache is called as secondary cache. L1 is called as a primary cache and L2 is called as a secondary cache. So, the why we require this? Why we need these caches? For a why we need cache?
For speeding up the accessing the data.
Yeah, temporary data will be stored here so that the CPU can perform the operation fast and it will be stored in L1 cache which will get updated in L2 cache and finally to the destination wherever you want to place the data, right? So the process will become fast. If you didn't have cache, then every time you have to store it in a destination and you have to also instruct the CPU go to this place, that place, right? So it's very tedious job and the processing also will get delayed. And then that for speeding up the process you have this and you have Snoop control unit. So you can see here SCU. Snoop control unit is for maintaining the coherency between L1 and L2 cache within the CPU. Means any changes updation happens in L1 that has to get updated in L2 also. For that reason we have Snoop control unit. It is a bridging between your L1 and L2 to maintain the data coherency. Then you have timer and counter here. Next section is timers and counters. Timer and counter why we require? For delay generation. You can use timer for what? Instead of for loop I will use timer for generating a delay. Okay. Say you want to blink LED. So you will insert a timer. For so much amount of time, LED has to blink. Now the image processing has happened. One way is you will see the time, the process the time. The other way is you can insert the timer as an interrupt. How much time it took to process the image, larger data. So we can bring up a timer. Okay. What kind of timers are available? How I can use this timer? So you have to initialize the timer. You have to tell the timer. You have to load the timer with this much amount of time, and then it will run for so much amount of time. Same like your for loop only. You have a variable I, you will assign the count and looping will happen. Similarly, timer also. You have a register associated for the timer. Take that register, load the value of in the timer, start the timer, keep monitoring the timer, stop the timer. So this is the process. Then you have counter. Counter is for counting an event. Suppose if a motor is running, if it has to run for so much amount of time, I cannot keep counting manually how much amount of time. So I will put a counter, how much time it has taken to finish the count. So counting operation is also required. Now for even for counting operation, we will make use of a timer only. Okay. So these are all attached to your CPU. Now you have GIC, General Interrupt Controller. So as we all understand, we need we need GIC. We need individual interrupt mask. We need interrupt prioritization. There are 5 peripheral interrupt. Okay, and 16 CPU private interrupts are also available. I'll be showing you shortly about that. And then we have DMA. DMA is also a part of this variant. DMA is for every time your CPU cannot take a task of transferring a data. If you have a huge amount of data and every time you will assign the CPU only that task, CPU will be held back doing that particular job. Instead, the intervention of the CPU has to be overcome by some other person, some other master, and that some other master, only master can be DMA. So there can be only 2 masters every time. One is our CPU, the other one can be DMA. So if you have to transfer data from one memory location to another memory location, and if you have a huge data transfer, then what you will do, the CPU will assign the work to DMA. How it will assign the work? CPU will tell DMA, you take over my job, and master is memory 1, slave is memory 2, and this much amount of data has to be transferred, length of the data that has to be transferred. Once the data transfer is over, give a flag signal to me, then the next process or the next person who is waiting to do a data transfer will be handed over. So there is something called as arbitration also, bus arbitration. One after the other, the priorities will be assigned and then the task will be taken care by the DMA also. That is also possible. To carry out all these processes, some kind of configurations are required. Okay, you have a configuration also, and you will have a very small amount of memory that is there indulged in this configuration block, because it has to have a track of the register, right? So that configuration details will be available here. Okay, these are all the components that are there, elements that are available here. For storage, when I talk about storage, yes, we need memory. So what all memories are available? We have 256 kilobytes of on-chip memory. Okay, we have 256 kilobytes of on-chip memory, and we all understand that it is RAM, and this 256 kilobyte is divided into 2 parts, 128 plus 128. 128 is allocated for ROM, 128 that is unmodifiable program, unmodifiable for booting purpose. Okay, your system, your OS has to be loaded. Okay, and all the default settings has to be done. Your IVT, interrupt vector table, has to be loaded. All these things has to be placed, correct? So for that you will have a program memory. wherein it will have a firmware written. It has a firmware that will support all the default locations. Okay, so you have ROM and RAM segregated here. Okay, and then you have another memory here. You can see DDR memory. Okay, so by default, whatever you work with this CPU will be placed in this DDR. As the name indicates, it is a dynamic memory controller and double data RAM. Okay, double data RAM, dual data RAM it is. Okay, it has different variants: DDR3, DDR2, LPDDR2. So they are all not compatible to each other. You should be very specific when you select DDRs. Okay, whether DDR3 is required, 2 is required, or low power DDR2 is required. Okay, then you have other small amount of memories that are there for flashing of the data and for storage of whenever you have some debugging techniques or some minimal the timers that it requires some amount of memory to be stored, some registers are required. Okay, so such cases you have a static memory controller and they are NAND, NOR and quad SPI. Okay, with this much amount of elements, it is not possible for us to come up with any kind of application, right? Because within this, okay, these things are available. But there is one more thing here: Neon or FPU engine, Neon or floating point unit engine. They are additional functionality to this ARM processor. Neon engine, no, it provides single instruction, multiple data facility. Okay, so it it is used for floating point operation, fixed point operation. It is used for you have a image, you have a DSP, you have a say some filter designing which has real and complex numbers. You have an image which has to be brightened, which has real and imaginary complex numbers, which can be loaded at a time and then you will get an output at a time. Some operation will happen and I'll show you the block design of that also. So you have a special neon or a FPU engine, floating point operation. But this much is not sufficient. You want to talk to outside world as well. So to talk to outside world, we need sometimes we need to have a communication media because ultimately your laptop has to be connected to the board, development board hardware. So how will I connect? I need some communication media. Okay, so we have other communication channels. You might get a data from Ethernet, so you need to have a Ethernet based communication. You might have a data inside USB. You might have a data as a you might want to see it or sense it via LEDs. Okay, you want to have more control over the device, you have push buttons. You want to have more control, you have a switches. Okay, because operational capability will should be based on a switches. So a manual switches are also available. Then you have UART for serial communication. You have CAN protocol for automotive applications basically, and then you have I2C and SPI. You want your system, your hardware to talk to another hardware, so you want to have communication between them. Then you need I2C. You have another module that is inserted on a hardware, and that module are communicated via SPI, serial peripheral interface, and inter integrated chip. So all those are available here. And this 2x refers to two instance of. So you can have multiple instance of the SPI devices and it will be named as SPI 0 and SPI 1. On a similar grounds, you might have single instance also. So that you will have to check once you start working with any of these devices. Okay, whether you have a single instance or a two instance of that particular thing. So with the help of these peripherals, we call it as a peripherals, you can communicate with the outside world. Okay, And you can observe that all these peripherals are a part of PS, are a part of PS. It is all not available as a part of yellow shade, correct? It is all part of PS. Then, can I access these peripheral? Of course, you can access this with to the external world. Can I access these peripheral inherently with the PL also? Yes, it is possible. You can access these peripherals to the PL side also. Now, whenever you want to access any of these multiple peripherals to the external world, it is accessed via multiplexing action. Multiplexing action. So you have MIO. I want to use only one SPI0 and I want to use GPIO. So these two will be multiplexed, enabled. Rest of them will be masked. Okay. So through that multiplexing action, you will be able to take it to a external world. The same peripherals, you want to access it here also on the PL side, it is possible. There are wires, chunk of wire, there are lines that are connected to the FPGA side also, and that is via EMIO. EMIO refers to extended multiplexed input output. Extended multiplexed input output. Okay, so these are the this is the block diagram of your Zinc 7000. And when it comes to programmable logic side, you can see we have XADC, okay, analog to digital converter, Xilinx ADC it is, and you have PCIe, okay, PCIe Express for it is also transceivers, okay, and you also have a memory here, and you have a millions of logic cells that are connected, and you can club these logic cells to act as a memory device. You can make these logic cells only. You can program these cells as per your logical requirement by writing an specific RTL code. Okay, so that is also possible. Now, as I told you, you can independently work with this PL and you can independently work with this PS, or you can have a combination of this PS and PL. Now, independently when you work with PS, fine. Independently when you work with PL, okay. But when you work with PS and PL, there should be someone who will help you to place a data or float a data from PS to PL or PL to PS. That action is carried out using AXI. Okay, AXI. That is what you are seeing here. Okay, slowly I will come to that one by one. So this is your Zinc 7000 detailed inbuilt diagram. Okay, so you have APU, 512 kilobyte of L2 cache, 32 kilobyte of data cache, OCM on chip memory 256 kilobyte, system level control registers are there. You need no registers because I want to load timer. I want to tell DMA that this is the master slave. For everything, you need some registers. Control registers are required. Then you have MMU, Memory Management Unit. This Memory Management Unit is for translation, for the CPU to understand. Okay, it is required for translating physical address to virtual address and vice versa. Virtual address to physical address. So that is the reason you have MMU, right? Then you have central connect. Okay, this central interconnect is switch based. Now this L2 cache is getting connected through this central interconnect, and through the central interconnect it is connected to. So only when the switches here are active, only those peripherals are enabled, and that will float a data to the cache memory. Then you have an external memory that is connected, and that external memory is DDR memory, and that external memory is connected to your programmable logic part also. So data flows in both the direction. Okay, both the direction. So there is an interrupt request also connected through the GMC. That means only if GMC is high activated, then only any of the interrupt here, you can work USB as an interrupt module. You can work with SD card as an interrupt module. You can work with the gigabit Ethernet as an interrupt module. You can work with UART as an interrupt module. Like that, any of the peripheral or any of timers can be worked as an interrupt module only if GIC is enabled. Else, you cannot work with the interrupt. Okay. Now, for everything to work in a very systematic way, you need a clocking system. So you have a clock systems also available. So as I told you, internally you have CPU, which has a Snoop control unit. It is acting as a bridge between your L1 and L2 cache for maintaining a coherency, data coherency. MMU is memory management unit, neon and floating point extension, and then you have a ARM Cortex processor. Okay, A9 processing unit. OCM is 256 kilobyte. So before seeing this, you should understand that APU, depending on the version of the device, you can have a architecture depends on the version of the device also, whether it is 32-bit or whether it is 64-bit. Okay, so depending on that particular variant, you can have a different APU. So APU is primary component. Okay, primary component. Neon media processor is there, and then floating point unit is there, memory management is there, L1 cache is there, L2 cache is there. Finally, Snoop control unit forms a bridge between L1 and L2, and some responsibility for interfacing with PL also, it is taken care by Snoop control unit. Okay, L1 and L2 cache are the primary and secondary cache, which will allow or permit the local storage of frequently accessed or required data and instruction. Why? For fast access time. Okay, and then L2 is of 512 kilobyte. MMU is responsible for translation of virtual memory address to physical. Okay, so these are the main elements that are there as a part of your APU. Okay, then you have Neon engine. So Neon is an additional, as I told you, it is an special functionality to your main ARM processor. So you look into any of the ARM processor, you will have this Neon engine. So Neon engine is basically used to facilitate accelerating the image, okay, or DSP type of algorithms, or any kind of video kind of algorithms. So it can be this this can be accessed by writing a C code. Okay, explicitly you can make use of this Neon engine. Okay, and you can write a C code for this, and then you can work with this Neon engine. This works based on a SIMD concept. SIMD means single instruction, multiple data. So you have two registers here, register A, register B. It will accept multiple input vector. Okay, so multiple input I can give here, and multiple input I can give here. Say suppose you have 2 plus 3j and another set is 5 plus 6j, 7 plus 6j, minus 8 plus 6j, and I want to perform addition on all these things. So all real-time data will be fed on register A, all imaginary type of data will be fed into a register B. And same operation will be performed on all. Okay. Say same operation means I want to brighten the image, I will enhance the image, plus I will do, or negating of the image I will do, or maybe multiplication kind of operation I'll do. Some kind of operation you are performing, some logical or arithmetic operation you are performing. The operation is same for all, provided operation is same for all. It can operate on a large number of data samples. Pixels, it can have a pixel simultaneously, and it will give you the output. And the type of operation is parallel. Okay, parallel kind of operation. So you have a FIR filter to be designed. So you have n number of bits. So you can perform the operation based on that. So your SIMD term suggests that Neon engine can accept multiple set of data and the operation can be performed using this digit. Again, generically, the size of the vector may vary. Okay. So the important feature is it has a lane. So you can see here lane 0, lane 1, lane 2, lane n minus 1. So which is performed on different set of input at a time. So it supports variety of data type, signed number, unsigned integer. It supports single precision data, floating point number, half precision, double precision. Okay. Single precision data means if you have a 32-bit data, in that 1 bit will be, that is MSB will be assigned for sign number. Rest 8 bit is for exponent, 23 bit will be for mantissa. So totally 32 bit. Half precision means 1 bit for sign number, 5 bit for half means 32 half, 16 bit. The data itself will be 16 bit. Okay. So double data means double. So like that, any kind of data type is supported by this Neon engine. Then you have FPU also along with that Neon engine. FPU is for floating point computation. So this also supports single precision data processing, and it also provides conversion from fixed point number and floating point number. So you will have a specific instruction for that, intrinsic instructions that has to be followed. Okay, so you have different kind of instructions that are there for accessing this. So these are the PS components. Okay, then you have APU. These are the APU components. So you can inherently you have another thing called as APU. Sorry, ACP. ACP is accelerator coherency port. So one is SCU. SCU is for maintaining a data coherency between L1 and L2 cache. ACP is for maintaining data coherency between PL and PS. PL and PS. It acts as a bridge between your PL side and PS side. Okay, because sometimes you are transferring a data between your PS and PL. There also cache will come into a picture. There also data coherency has to be maintained, right? So that kind of a data coherency is maintained by your ACP. That is accelerator coherency port. This is tied to PL, okay, via PS interconnect. Snoop control unit will regulate memory flow, providing cache coherency. Okay. APU is the heart of the processing system. Then you have MMU. Translation will happen. It supports translation tables will be stored. Translation tables will be stored in your main memory. If I write 16 KB, it is understood as a binary for your CPU. Okay. So that kind of enablement of the data cache is required in the memory, many of the system. Then you have this as a processor cache, L1 cache and L2 cache. L1 usually it will be smallest in size but fast access. That's why it will be 32 kilobyte. And L2 will be larger cache. It is used both for instruction and data. Okay, 512 kilobyte. So cache coherency has to be maintained, and this is a bridge which is internally connected to data cache of this end, because instruction not required, maintaining the coherency between the data is required. So you will have a connection between the Snoop control unit to and for the data cache only. So if the cache line is updated, if any of this cache line is updated, so SCU will know. Then it will take the updated cache line from the CPU. Like that only you have ACP also from PL or to the PL. Okay. it is connected to the Snoop control unit, which is in turn connected to the caches. So updation will happen through if there is any changes from the PL to PS side also. When I talk about a memory, two memory interfaces for external DDR memory. It supports LPDDR2, DDR2, DDR3. Other than that, you also have a support small memories that are there, NAND, NOR flash, QSPI, and SRAM. Okay, and then you have two embedded memory components, on-chip memory, SRAM, and boot RAM. Okay, all these are available. You want to control the PS behavior? It is controlled via SLCR, system level control registers are there. This system level control registers are required, there are various registers available to control. Something like you have PLL register, you have clock register, you have DDR register, you have peripheral register, you have MIO register. These registers are used to configure PS. What configuration? Say you want to do power and clock management. So a configuration will happen. Clocks will be distributed, to PS and PL. Okay, separate clock for PL, separate clock for PL, separate clock for some of the peripherals, separate clock for memory, separate clock for CPU one, separate clock for PL side. So these management and configuration is done with a set of special register. Okay, there are categories in the special registers also. Categories means, so DDR control registers are there, DMA initialization register is there, timer initialization register is there. They are not locked upon completion. Okay, the user will be exposed to them, and you can work with the special function registers via software manner. You have to write a program, you have to initialize, you have to understand the name of the registers. Like whenever we take microprocessor or microcontroller, we'll have the name of the registers, A, B, R0, R1. On a similar grounds here also there are a register. Some of them are named as usual, R0 to R1, R12, because this is ARM processor, no? So you will have a R0, R1, R2 up to R12, R13, R14 are also available. Those are common registers. There are some special function registers also for controlling the action of the timer, for controlling the action of UART. Why I need to control the action? Because it is designed for multiple rates. It is designed for, because you have different timers. Now I want to tell CPU which timer I want to use. I want to instruct a CPU to what time it has to work, when it has to start. So you will have one bit assigned, through which your CPU will decode it and understand that, okay, this much amount of time I have to start or work. And when I talk about your baud rate, it works with different baud rate. So if you are displaying something, some text with some baud rate, and you want to display it with some other baud rate, okay, or your module, depending on your hardware module compatibility, you will see the compatibility to what baud rate it works. Then you can configure your here with that particular baud rate. So all those are required. So you have a special registers for that. Okay, then you have all these peripherals. Okay, so these peripherals are used for, as I told you, you need to understand why I need to use these peripherals also. Correct, no? So until and unless you know what is the usage of these peripherals, you will not be able to use it, right? So I have to understand why and for what these peripherals are used for. So your Zinc SoC supports all these IOPs. They are also called as IOPs, input output peripherals. Okay, and there are two instances, as I have already mentioned. So you can notice here static memory controller. Static memory controller is actually a PS memory interface, but it is shown with your IOPs because it shares the same MIO. Okay, even though it is inherent to this, it is shown explicitly. Okay, because it shares the same MIO connection. Okay, it is something, it looks like a IOP only, input output peripheral only. Now you have USB. USB means there are two USBs. Simply USB, if I understand, no use. I should know that which type of USB it is. It may have 2.0, that is OTG device, okay, on the go device. So it will allow the device to do bidirectional transfer. Okay, what kind of things I can connect with USB? I can connect camera, I can connect smartphones through this USB plug, yeah, through this USB channels. Okay, then we have Ethernet, gigabit Ethernet. Gig Ethernet means gigabit Ethernet. Gigabit means 10, it supports 10, 100, 1000 megabits per second also. Okay, this is for Ethernet design. So generally it supports by default 2.5 gigabit ports. Okay, so if I connect Ethernet cable with this, no, I can get a data through Ethernet, and then I can put it on some memory location. Okay, some streaming of a data is happening via Ethernet. That is possible. So then I will make use of these channels of gigabit Ethernet. We will implement Ethernet design. Then you have SD, SDIO here. You can see here, no, with the DMA. You have to use this with the DMA. SD means secure digit. It is something like your memory card only. Okay. What kind of functionality it can incorporate? It can incorporate functionalities like Bluetooth, okay, then Wi-Fi, some image I can load in SD card. Okay, what you can do is I will show you now. Boot image you can create. Your programs boot image you can create. That boot image you can store it in SD card, and then you may not require this ID. You have an image on your SD card, you can run it on a hardware. So if you have a robotic application or something, you want to place this module onto any of the electronic gadget, you cannot connect with the laptop based environment always. You cannot keep it connected, right? So there are different modes to check with the working, testing, demonstration. JTAG mode is fine. To have this system onto your hardware, and you want to place it onto some of the electronics gadget, and you want to move it to any location, okay, portability if you want, then SD card is there. So you have SD card access, secure digit. So you have placed your image, the code, okay, the final output image onto SD card, and your ICE chip will work as per that image. Okay, details of the image will have all the hardware and software details. So it will have a binary file. Okay, it will have all the image files that are there. Based on that, you can work. So you will have a SD card slot onto a chip, onto a hardware. So you can place and work with that. So that advantage is also available. Then we have two CAN protocols, right? Two CAN protocols. CAN also, and you have SPI and you have I2C. So when you talk about communication protocol, these UART, SCAN, I2C and SPI will come into a picture. They are common hardware interface which you can use, and it follows its own protocol. Protocol means if I take UART, I should understand UART will have two pins, TX pin, RX pin. That can be two variant depending on UART module that is placed. So you can have two TX pins, two RX pins. Okay. TX pins, you all understand, transmission will happen, RX pin receiving will happen. So universal asynchronous receiver and transmitter it is. This UART, another feature is it works on baud rate. Okay, it works on baud rate. Baud rate means bits transmitted per second. Okay, number of data transmitted per second, that is baud rate. There are some standard baud rates, but when you program anything here, you have to understand to which baud rate you have to transfer the data to the hardware, because the hardware module, UART module that is there inherently will accept which baud rate. Baud rates between the laptop and the development board should match. Then only easy transferring of a data from your PC to the hardware will happen. If baud rates are not matching, then the transmission will not happen. Okay, that is UART. By default, serial communication, it does serial communication. All these are serial communication device. Then you have I2C. I2C I2C does not have any pin like TXRX. I2C will understand only one thing, that is master and slave. So you have to give a master address and a slave address. The here also same SPI also it can understand as a master module and a slave module. But only difference is this SPI will understand only one module as a master at a time, and whatever you connect will be a multiple slaves only. So it can have only one master. When you are programming SPI, only once you assign allot anything as a master, that will be a master always. But in I2C, master and slaves are interchangeable. If I have CPU and UART or CPU and DMA, sometimes CPU can be a master, DMA can be a slave, DMA can become a master, CPU can become a slave. So the translation is possible in I2C. So if you have two microprocessor connected, one will become a master, another will become a slave, and after some time another one can become a master and slave, like your joystick based operation. So you can program one machine as a master, another machine as a slave. So as per your joystick movement, your slave robo will move ahead, come back, something like that. But SPI, always one will be master, one will be slave. CAN protocol is for all uh, automotive based application. Like you have an industrial based application, you will use the CAN protocol, because those protocols are designed for that aspect only. Okay. So these are the main things about what kind of usage. Okay. How I can make use. Of course, all these, no, so you have to check with the voltage ratings also. Now simply I cannot come up with a stepper motor of a very high voltage and connect it to any of these peripherals. That may not work. So I may need in between the translation of the voltage. Correct, no? So you need to bring down the voltage level. So that is also required. So you have to check with the bank voltage level. Each are selectable maximum at 3.3 volt. Beyond that, I cannot connect any other external device. If you are using external device, be careful and connect it to a suitable value. So you need a driver for that, which can perform the conversion. So which can increase the voltage level, okay, and then fed it to like LM 30 LM driver is there, no? IC you can use, and then you can connect it. Okay. Like that, you have MIO, and each are accessed as a MIO pins. You have 54 pins available, 54 dedicated package pins through MIO. Like that only through EMIO, 64 pins through EMIO. You understand, no? So 2 to 4, 5, 6, 7, 8, 9, 10, like that. You have 54 pins which can get connected to the. Now everything will not be populated, because at a time, everything you will not connect, no, at a time. Some pins you would have connected, some pin you would have not connected. So some ports can use EMIO also. Okay. EMIO is extended interface to PS, input output peripheral. So some of the pin are connected through this. There are two lines. So if this line is enabled, this line will not be enabled. If you want to use this SPI on PL side, then this line will be enabled. If the same SPI you are connecting it to external world, this line will be enabled. Something like that. Okay. These interconnects has to be handled carefully, when I connect external device, plug in external device, I need some kind of communication that should happen. Otherwise, I will not understand whether the connection is successful or not. So the interconnect has to be, whenever you enable the data transfer between PS master and PL, some kind of acknowledgement is required. And how much amount of data I am transferring, that is also important, no? So because pre-designed, it is all pre-designed. So it can handle only 8-bit of data, means I can transmit only 8-bit of data at a time. Your UART TX can transmit only 8-bit of data, means I can transfer only 8-bit of data. But if you have a huge amount of data that has to be transferred, then you have to break the entire data into two parts. Send LSB first and then MSB. That will be understood by the user how he has programmed. So that way you have entire 16-bit, if you try to transmit with a 8-bit amount of data, it is not possible. These are all memory that are available. Clocking. When I talk about clocking, simply you don't have one clock structure which is providing a frequency to CPU as well as other peripherals. No, it is not like that. You have a different clock, first of all for PL, different clock for PS. When you plug in your system, when you turn on your hardware, PS will first boot. That is, ARM processor will turn on first. Then your PL will boot. Then your PL will boot. So the clocking is provided separate for PS and PL. When you see PL, you have IO PLL, ARM PLL, DDR PLL. They are also, again, you have a divider circuitry, because IO PLL may give me some frequency, ARM PLL may give me some frequency, DDR. If I want to work with a high frequency, then I may need, this frequency is not enough for me. I will join these two, I will club these two. I will get some 200 to 300 megahertz. Then I will connect it to some required inputs out. Okay, connect it as an input to the required peripheral. So the multiplexing action is there. And then if that frequency is too high for me, I can divide the frequency. So if that is too high for me, as it is the frequency that is coming, then I can divide the frequency also. So you have a divider frequency also. You can select and divide and then feed it. Like that, you have a provision of selecting 4 clocks at a time, 4 different clocks, customizable. You can define the frequency. Okay. And you can use all the 4 clocks, or you can use any of the 2 clocks, or you can use any of the 3 clocks, or you can use single clock at a time. Okay, so that is possible. PS clock source from external package pin, like you have a quartz crystal oscillator, analog circuitry you will have. From that you are getting a PS clock. Again, that has 3 PL fixed it is. Okay, and synchronizing the clock between PL and PS is taken care by the architecture of the PS. You need not worry about the synchronization. PL cannot supply clock source to PS. PS is already booted. It cannot supply a clock source to PS. PL will boot next. Okay. Next part is programmable logic. This is the second principal architecture of part of the Zinc architecture, programmable logic. Okay, so like your processing system, you have programmable logic also. So as we all understand, so yesterday you have already understood the architecture of this programmable logic also. I need not talk much about the architecture of this programmable logic. Okay, so you have PS as well as PL part. Hmm? So PL consists of your CLB, which will have a slices, and then it will have LUT. Each slice will contain LUT and flip-flops. You can perform the logical design as per your requirement. And there are software drivers that are available. For each and every peripheral, you include in your hardware. Like GPIO, if I include, you will have a driver for GPIO. You have included UART, you will have a driver for that. You have included CAN protocol, you'll have a driver for CAN. Okay, you will have a drivers. So common standard services are configuration is given for you. Device ID will be, these are the structure that you can actually use, and these are the structure and properties that are available that you can use it in your design. I will show you this on the tool itself. Then these are the common strategies service example that you can use. Okay, you want break for 5-10 minutes? You have any doubt you can ask? Any doubts?
Yeah, if participants have any doubts, they can directly unmute and they can ask to Asha ma'am, or else they can type it in the chat box. Yeah, ma'am, you can schedule short break, no problem.
Yeah, you can take break for 5 minutes. We'll get back at 11:25. Fine?
Yeah, sure, ma'am, sure.
Sure. Thank you. Shall we get started?
Yes, ma'am. Yes, ma'am. Please start.
Yeah. Now I would like to show the same thing on the tool itself. Others ready? Any doubt you didn't ask? Okay. Just give me 2 minutes. Hope my screen is visible of the tool. Screen is visible, right? Yeah. Thank you, Praveen. Okay. So now, okay, how the AMD will expedite the design flow of any embedded system. Okay. The design flow of any embedded system is taken forward using Vivado and Vitis. Yesterday you would have seen Vivado design suite, which provides features of Xilinx FPGA and SoC hardware design. And it also includes, we were able to write the code either in Verilog, VHDL, and then edit the code, synthesize the code, implement the design, simulation is possible, and then binary generation is possible. Hardware designing is possible using this Vivado design suite. Also, this Vivado design suite will provide the PS configuration. Okay. Uh, we can perform the code generation initialization also, and Vivado design suite has uh, different editions also, different versions of Vivado design suites are there, and it supports a different architecture, like whichever device you are using, that particular architecture it supports. So you can that is how the AMD design tools will take us through the design process. And then so finally now we are doing an embedded system design, and hardware design is done using hardware, so Vivado. Okay. And then you have Vitis software platform. I will invoke now. Vitis software platform is used for software development. So you can write C code, C++ code there. Okay. And you can debug the software application using Vitis environment. So these are the two processes that are used. So the moment you invoke Vivado, okay, you will get option of quick start, create project. Okay. So you can go to create project, select a suitable location. So on the desktop, I have already created a pink lab, and then in that hardware I have created, I'll make a new folder. Okay. I'll say project underscore pink. I'll write and then say, okay, this is a hardware lab that I am trying to show you. In that, the name of the project can be changed or retained as it is. Go to next. Very much you are doing an RTL project. It is not a post synthesis project, or IO planning you are not doing, or neither you are taking from an example project. You are trying to create a RTL project. You can go to next. Next. I'm not going to write any RTL code as such. Instead of selecting a part number, we will advisable to select the board. Okay. And the board that you have will be pink Z2. Okay. ZU board, whichever board you have, you can select that particular board. Okay. Then go to next, then finish. So this is how the board appears. Okay. The board looks like. So you have a project summary here. If you observe this, even though you selected pink Z2 of this part number, product family is Zinc 7000. Okay. And then board part name, board revision. Okay. All these things will be specified here. And the project location. Okay. So you can further go to settings here. Now I'll be telling you all the things that you can modify or use it in the tool. You can go to settings. Here, by chance, if you have selected wrong board, you have a provision of changing the board here. So you can select this 3 dots, rename the board. Suppose if you wanted, you want Z board or pink, any other variant board, you can change it and then say apply. Target language, you want to write a Verilog or VHDL code, RTL code, then the language selected by default here was Verilog. So if you wish to select VHDL code and if you are comfortable with VHDL coding, you can select VHDL. So all these modifications can be done. Once it is done, you can say apply and then OK. Okay. So now, as usual, I have not made any changes. I am using it as it is. So no need of changing anything. Okay. Then once this is done, yesterday you would have seen, you would have gone to add sources and then create an RTL, correct? So now today what I'll try to do is I will try to create a block design using the IP integrator. You have a IP integrator here, flow navigator. You will select this create block design. Retain the same design name or change it if required. Then say OK. So now you have here the toolbar menu wherein you have this plus symbol. You can select any of the IPs, okay, intellectual properties that are given here. You can create your own IP also, okay, that is also possible. And then you can create a custom IP and then you can add it here. Now, for us to come up with an embedded system design, I need CPU, correct? Processor, processing system you need. So, depending on the board that you have selected, you have to write that particular processing system name. So, Zinc 7 processing system, I'll include this, which is available as a IP. Okay, which is available as a IP. Now, you can customize this. Okay, when you double click, you will get to see the block diagram, which I explained you, on the slides. So you don't need any slides or any other material. Everything is available here itself. Okay. You can just check for the board you have selected. This is the APU, ARM Cortex A9 you have, and it is a CPU, 2 CPUs you have, and you have SCU, you have all these OCM, GIC. The difference is the one that is highlighted in green, they are all editable. The one that is not highlighted in green, you cannot modify that, correct? So you can edit all these things. Instead of editing, one way is nothing is checked here. That means none of these are selected. I'll cancel this. Now when you expand, when you check, there are multiple things that are visible here. Correct, no? Multiple things that are visible here. Can you keep making connection one-to-one? It is very difficult, very tedious also. So we have a designer assistance available. The moment you place this IP, go with run block automation. Go with run block automation. The very first run block automation will allow you to make some mandate connections. Now, mandatory connections means what? Mandatory connections means clock. Mandatory connections means UART connection. Because ultimately you will connect it to a hardware and you need serial communication. So UART connection mandatorily that will be enabled. Like this, mandatorily some memory which will be the default memory location that will be selected. So all such things will be selected by default. So further, if you want to change, replace, you can do that. So better to go with this designer assistance run block automation that is provided to you. When you use this run block automation, see here DDR, okay, has is evolved here. And then fixed IO, some fixed input output pins, MIO, see here, DDR, VRN, VRP, positive and negative. And then you have PS, some of the ports that are enabled, AXI ports that are available. So all these are done by default. Connections are done by default. Now, if you don't wish to do this, then you can do the configuration by yourself. Okay. If you are not willing to perform run block automation. Now you just double click on this and see here some check marks you can see. When you can see some check marks, these peripherals are selected by default when you said run block automation. UART 0 is selected, GPIO is selected, SD 0 is selected, USB 0 is selected, ENET 0 is selected. Okay, now further configuration if you want to do, you can go through this page navigator. So first one, whatever is given here is a block design. Okay, check with the summary report if required. Then you have PSPL configuration. Second line is PSPL configuration. Now when you check with this PSPL configuration, that means when you are enabling doing something configuring something here, that means you are involving both processing system and a programmable logic to perform some kind of a data transfer. Okay, so that is the meaning of this. So when you expand this one by one, general information will be given here. So which is a UART that is selected and what is the baud rate. So you can expand this. So this UART 0 and UART 1, there are two instances of UART, and this UART 0 and UART 1 both have baud rate of 115200. Okay, this is the baud rate. So that means when I try to run the code onto a hardware, make sure that you set a baud rate of 115200. Okay, then you can change this to different baud rate also. See, you have other baud rates also. Starting from 4800 to 9600, 19200, they are all standard baud rates. Similarly, if this is selected, this will also give you different baud rates. Then PN idle port. This is a signal, AXI signal. Okay. Now, since I mentioned AXI signal, what I should do? I should be able to explain you what is AXI. Okay. So, I will take some more time to explain what is AXI. Okay. AXI means what? Why you will get to see always AXI in the all the configurations when you do, and what is this AXI all about? So you have something called as, when I talk about a microcontroller, you have something called as AMBA protocol. AMBA, AMBA. AMBA means Advanced Microcontroller Bus Architecture. What is this Advanced Microcontroller Bus Architecture? It is a open standard connection for functional blocks that is there on the system on chip. Okay, it is a standard which will help you to perform the connection between different functional blocks. It could be PS, PL, it could be within PS, it could be within PL. AMBA is a protocol, bus protocol. Okay, its specifications are free. Okay, platform independent. It is platform independent. It is not dependent on the platform. It can be used with any processor architecture. Okay, it can be used with any kind of processor. In this AMBA is divided as APB. There are different classifications of this AMBA: APB, AHB, AXI, and ATB. Okay. APB means Advanced Peripheral Bus. It is for low power, and it will allow low bandwidth. It is for high performance. Okay, it is for high performance. It is very compact, not extendable. So whenever inside microprocessor, suppose you have DMA controller and then something else has to be internally connected. So you have a switch matrix that is getting connected to the DMA controller. Then that kind of a minimal connections within the microprocessor will get connected through APB. So it is because it is compact, but it is low power also. So that is the use of this APB. When I talk about AHB, no, AHB is high performance, advanced AMBA or AMBA high performance bus. This is mostly used in Cortex M processor, microcontroller based application processor, and other low latency SoCs. This AHB is used. The next one is AXI. AXI is Advanced Extensible Interface. Extensible Interface. It is for high frequency, high bandwidth, and also it is used for a wide range of devices that is connected from, which is used for connecting between the two functional. It is a protocol. It is a way of signaling through which the module will talk to outside world. Module can talk to another module. So, and it is a tailored design for SoC. Okay. So whenever you want you want any two functional block, or you want to have a data transfer between PS and PL, you have to obey AXI rule. AXI interface will be added to the module. Okay. Then the third one, the last one is ATB. ATB is Advanced Trace Bus. Okay, trace bus. This is for carrying a trace data, like a trace buffer. So we are not going to use that in our any of the SoC design. So we'll not talk much about this ATB, and that's why it has been masked also. So few of the signaling are done using APB. Rest few, maybe few, very rare AHB, and almost all the communication happens through AXI, Advanced Extensible Interface. Okay. So this Advanced Extensible Interface has three basic concepts. Okay. This AXI has three concepts which you have to understand if you are performing, or if you are designing your own IP. You need to understand all these things. What are the three basic concepts? AXI master, memory map, AXI stream, AXI light. Okay. AXI light. So these are the three interfaces that are available whenever you go with the AXI, Advanced Extensible Interface. So AXI master is for AXI memory map or full is for multiple data if you want to communicate. Means I want to have, I have a huge array of data that I want to transfer it from one memory location to another memory location. Then we will need AXI memory. Okay, it will be designated as memory map. Okay, if you have a stream of a data, so video processing is done, you have a stream of a data that is coming in, then you will have you will connect with the AXI stream. Means It is all point-to-point connection. Communication is point-to-point. Streaming of a data from one master to slave. That will happen. So streaming of a data is always one-sided. Only one master to slave. But other two are bidirectional. Okay, other two are, this is unidirectional. Then you have another type of interface called as light. Light means if you have a single data, suppose LED, I want to blink, turn on and off one LED. You have a single data to deal with. Then you will go with AXI light. Okay. These are the three interfaces that usually you will see. And while creating a custom IP also, either any of these three you will use depending on your design. Okay. Now, whenever I talk about AXI, it has three main things. Okay. Those three main things are, it has three main concepts. One is master concept, slave concept, and interconnect concept. These are the three things. Now, when I include in a design any two modules, and simply if you say run block automation, some AXI will come into a picture. Okay. So you will have master, you will have slave, another one is interconnect. So always there will be a transaction from master to slave or slave to master. Okay. Transaction can be write transaction or transaction can be read transaction. That means when you talk about a transaction, it is nothing but an operation through which you are writing a data or through which you are reading a data from one point to another point. Always master will initiate the data transaction. Slave will respond to it. Slave will respond to it. Okay. So whether you are reading, master can read the data or it can write the data to the slave. Okay. So all these are important. Now, the third thing that comes into a picture is AXI interconnect. AXI interconnect will come into a picture. So you have multiple masters and multiple slaves that you have connected. It is not that I will always use UART only or I will use GPIO. You can have multiple slaves. No, I can have Ethernet, I can have SD card, I can have I2C in my application. You can have multiple things in your application. So when you have multiple things here and here between the master and slave, some person comes in between and that person is called as AXI interconnect. This AXI interconnect will do many jobs because it will have a memory inside this which stores the address of all these slaves. So when you insert UART along with your CPU, this AXI interconnect will understand that you identify the UART with something should be there for identification, and that something is address. So this postmaster will understand the slave not by the name. You can give any name to this. It will understand this slave by the address. It will understand this slave by its own address. It will understand this slave by its own address. Like that only, you have two master here. It can be, if there was one master, fine. DMA also can be sometime master. And CPUs are also two. Correct? So this will understand this also with address, this also with address. Everything here is memory mapped. Memory mapped. Everything is identified by the address. What happens in that address? That address, the moment you access this, whatever you write here, whatever you do with this slave will be allocated in that address map region. How many bytes of data you are trying to send, what is the information you are trying to send, everything will get loaded in that memory region. You can write into that, you can read from that. Whatever you want, you can do that. That kind of job is handled by AXI interconnect. Okay. So the AXI interconnect will be inserted whenever you come up with a connection which have multiple data and multiple slaves to be connected. It is responsible
So in a simple word, this AXI interconnect is responsible for connecting master and slave. Okay, master and slave. AXI interconnect is there, no? This will be slave for the master. This will be master for the slave. If you look at this, okay. Now, fine. You have master, you have slave. Master can send the data, read the data from the slave. Both are possible. Okay. Everything will not happen simply. It will happen with respect to clock. So you have a systematic clock and you have a information that you are sending or receiving. But this information will be sent or received only when two signals will become active high. And those two signals are valid and ready. Valid signal understood by master, ready signal given by slave. So master, once it identifies UART with the proper address, appropriate address, or GPIO with appropriate address, it will set itself giving a signal valid. Oh, valid slave is identified. Once that valid is identified, then this slave will give a signal ready. Yes, I am ready to receive or transmit the data. Then ready will become high. Only when these two are high, our information will be sent. This may usually happen in 4 clock cycle. So like this, for reading the data 4 clock cycle, for writing the data 4 clock cycles are required. Like this, you have 5 channels. Okay, 5 channels. One is write address, write data, write response, read address, read data, response. First, when your master wants to identify a slave, first what it will do, it will look for the address. Okay. So whenever your AXI master wants to perform any kind of operation, what happens? First, it will write the address through write address channel, AW, and it is identified as AW. Once after writing the address, slave will respond by giving a signal, read signal, through which whether your slave is ready to read or not. Then finally, whether write data is happening or read data is happening, that will get enabled. Okay. So this is the job of your AXI interconnect. So you have clock. First, for address, you have 4 clock cycle. For reading or writing the data, 4 clock cycle. So first to identify which slave. Next, to perform the final operation. But whether it is address or the data to be read or written, all the things will happen only when valid and ready are high. Okay. So these are the important things to be known. So totally 5 channels are very important. Address read, address write, data read, data write, and then response signal. 5 channels are very important. Like that, your Zinc device supports 3 different AXI transfer, burst, light, and stream. And you will have a PSPL interconnect via this interface. So you will see M underscore AXI underscore GP, S underscore AXI underscore ACP, depending upon which peripheral you are including. GP refers to general purpose. M refers to master. AXI refers to AXI protocol. S refers to slave. ACP means accelerator coherency port for bridging and performing a data coherency between PL and PS. Excuse me. Like GP, you have another ports channels HP. HP means for high performance. Suppose if you bring DDR or DMA or BRAM, okay, block RAM, which is a part of your FPGA, into a picture, then high performance is required. If you take suppose LED or push button or switches, then general purpose is enough. Okay, so like that you will have these interface. Like that totally there can be 9 interface, 12 interface. So if you say take the slave connect, one will be master on the PS side, another will be slave on the PL side. Sometimes this will be a slave on the PS side, master on the PL side. If it is master on PL side, it will be recognized as M. Okay, if it is slave, it will be recognized as S. So if this is identifying, if it is looking for the slave, if this is a ACP is a master here, because it is situated in programmable logic side. So it is master there. If it is looking for a slave, it will push out this signal S underscore axi underscore ACP. So that is about AXI. So when you look into this block design, you will have AXI ports. Okay, AXI ports. So I'll show you that. PSPL configuration, if you go, you have, when I minimize general, you have AXI non-secure enablement. So if I expand this, you have general purpose master AXI interface. If you expand that, you have two general purpose, two instances are there. One is M-AXI GP interface, M-AXI GP1 interface. This is already enabled. If you want to include any of the peripheral, then it will look for the slave. If you don't want, you want to work only with the processor, if you don't need that, you can disable this. If you don't want M. If you disable this is there, no? This will go off, which was included by default. Okay. So now if you simply want to print using UART, I don't need this. If I want to connect any GPIO, then I may require this. If I want to connect any slave, any other IP, then I may require this. Otherwise, I may not require this. Like that only you have GP. Okay, general purpose, master, slave. Slave also you can include. And you have HP, high performance slave, and high performance master. Like that you have 4 interfaces, 3 interfaces, 2 interfaces. Okay, so you can enable or disable those. So which is available at this particular point. Then on a similar grounds, you have DMA controller, peripheral request interface 0, 1, 2, 3. Okay, which will support DMA capability. Okay. Then you have cross trigger interface. You would have seen this yesterday. You can select enable any of this PSPL. Then if you come down in a page navigator, you have peripheral IO pins. Peripheral IO pins, if I see, you have quad SPI. Are you going to use it in your design? If you are not using, remove this. As I told you, you have SD card. Like that only, you have another small memory, quad memory, and you have a flash memory. So you can download your image onto a flash also. If I have onto a flash memory, which is a part of your board, then also you may not require your system. Correct? Then if you are using Ethernet as a peripheral, then you can keep this. Else you can disable this also. If you expand this Ethernet, you have MDIO. Okay. So you will understand that I told you, no, how many MIO pins are there? That many MIO pin you can find here. So I told you, right? 54 MIO pins are there. I mentioned you. Correct? MIO pins are 54. Like that you have 0 to 53. In this 0 to 53, to which pin numbers your Ethernet is connected? It is connected from pin number 16 to 27. Pin number 16 to 27 is assigned for Ethernet. If you are using it, read. Like that only for USB, which pin number is connected. So you can make out. For SD card, okay, if it is enabled, it will highlight in green. If it is disabled, it will not get highlighted in green. SD card pin numbers 40 to 45. Okay. Then I have disabled this also. I have left only UART enabled now. So UART 0 is connected to which pin number? It is connected to pin number 14 and 15. One for TX, one for RX. Okay. So that's how it is getting enabled or disabled. You can enable 14 and 15. If you expand this, you can see the modem signals. Okay. You can see the modem signals. Like that only you have UART1, I2C, CAN, so on. Then if you come down, you have a MIO configuration. So MIO configuration, you have peripherals, memory interface, IO peripherals, APU and programmable. Here you can expand, quad SPI is selected. You can expand, you have UART 0, MIO pins 14 and 15. You have a provision of changing this. Okay. Then you come down, you will have a clock configuration. When you get into a clock configuration, you have processor clock, ARM PLL 650 is a requested frequency. So by default, if you get into a basic, these are the basic clocking, CPU clock, DDR clock. If you expand PL fabric clock, I showed you, you have F clock 0, 1, 2, 3. If you are not using PL, any of the PL part, you need not enable this. You can keep it disabled only. If you are not using any of the PL part. If you are using PL part, then you can enable, keep this enabled. Then IOPs, you have all these input-output peripheral. Depending on which you are using, the frequency can be edited here. Okay. Then expand this, you have a clock. External clock can be connected and it can be configured. Then you have timers. You have 3 main timers here. You can see here. Watchdog timer, triple TTC. TTC means triple timer counter 0, triple timer counter 1. Now, what is the usage of this? Watchdog timer, CPU timer it is. The moment you turn on your system, there will be a check on all the software updates. That is done using watchdog timer. If any of the fault occurs, resetting will happen. Then you have triple timer counter, TTC 0 and TTC 1. You can use this TTC for your application. You can also check with the frequency. Okay. So why this TTC is for? TTC is for waveform generation. Suppose I am doing some power electronics project. Okay. And then you have say you want to generate some PWM pulses for firing circuit. Okay. Firing circuit. At that particular instance, it has to rotate and then stop. If you want to do all those things, then you may require TTC for a waveform generation, for a square wave generation, for a triangular wave generation. You may require triple timer counter. Else you may not require triple timer counter. You can make use of watchdog timer, or you can use this for normal timing delay generation also. Then you have DDR. So DDR, if you expand this DDR configuration, DDR3, you should not change the type of the memory interfaces. Okay, because no DDRs are compatible. You can only check with this DDR settings. Check with the DQS to clock delay. If it is giving some other value, you can see default clock delay is given here. Change this to default values. Okay. Change this to, otherwise the path will get delayed, subtracted, and you will get a negative clock skew. Then say okay. So this is how we have. Still there are some signals. If you want, you can remove those signals, else you can. So I just want to print something out of this. Okay, I'll write some software code to print. I need only UART, and that is enabled UART. So UART is enabled. Rest all I have removed. One GPIO is enabled and one UART is enabled. Okay. Once the design is through, then you have on the toolbar menu, you have an option verify. or validate the design. Validate the design. It is always advisable to validate so that you will have no warning or any critical warning or error. Then say OK. Once that is done, here you have a source field. Expand the source field. Select this design .bd. .bd refers to block design. Okay, block design. And then right click and wrap up. Before that, if I want, I can add some other things also to this. Some other things means on the PL side, whichever, all these are the IPs that are available, which is some of which are connected through the to the PL. Suppose if I want to connect GPIO, okay, or UART, some UART you want to connect, or you want to connect BRAM, I can do this. But if you connect BRAM, okay, and try to perform run connection automation, see, it may throw the error. See, these two are not connected at all. They are isolated. Why? You think now. Why means because in this, I have removed, see, I have removed this master AXI connection. So if I enable this AXI connection and then say OK, and then one more thing I have to enable, that is if BRAM is PL side, BRAM is a block RAM which is available as a part of PL. If I connect that, I need to enable any one of the PL fabric lock. If you have not enabled, again, that also will give you error. So I have enabled almost all the required things. Then I'll say yes, okay. See, the connections are complete now. When the moment you make a connection, regenerate the layout. It will look in a systematic way. So you can also expand this and check in a more detailed manner. So this is only a generator. It is generating the signals. So this BRAM I have included, it is a dual. Okay. So it is a, you can configure this. So you have two interfaces here. I'll make one interface. It will look something like this. Here also it has two interface. I'll make it one. So you can change that option also. Port A, port B, you can enable or disable any one option. Other options are also available. So depending on the program or a problem statement that you have, you can enable or disable this. Now when you look into this, AXI interconnect came into a picture, that is Smart Connect. Now AXI Smart Connect came into a picture. The same, I'll do another design 2. I just add here Zinc 7 processing system, and I will perform run connection automation without deleting, enabling or disabling anything. I'll add GPIO IP. It is available as AXI only. So you have to make an AXI based, AXI port only it is available. If I make a connection here and arrange it, see this, here you have AXI interconnect. But when you saw open block design 1, if I open, you have Smart Connect. Both are same, both are alike. If you have a multiple things connected here, networking of connections if you have, Smart Connect will come into a picture. So here we don't have such networking. Such networking we don't have. We have only one sole IP that is there. AXI, it is connected through the AXI interconnect. When you expand this slave or master, you can see here valid, ready, valid, okay, and then last valid, ready, valid, ready. So for every address and data, you will have valid, ready, valid, ready. So that's what I showed you. You have valid, ready, and then other acknowledgement based signals. Okay, all these signals will come into a picture. Now you cannot make a manual connection for this, so you have a run block automation that is available. On a similar grounds, you can expand this master also. You will have a AR valid, read valid, address read, address write, B read. Okay, that is acknowledgement, correct? Then you have W last, valid, So all these are the AXI based signals that will come into a picture. Okay, you can modify this as per your requirement, which AXI you want, which you do not want, and then you can perform the simulation also. So another block came into a picture that is called as processor reset. You included only one block and this block. You included only this and this. Correct, no? You included only two. But rest two came into a picture automatically. So you have another block, processor system reset. This processor system reset means we need reset, no? We need reset. Correct, no? Why we need reset? Why we need reset? You people are there?
To bring the system into valid state.
If reset is not there,
If the system
what?
do invalid state, it unable to recover that its valid state.
If you have reset, no, then you can restore the device to its original state. If you don't have reset, then you will not be able to restore back. If reset is not there in my system, I will not be able to restore back to the original state. So that means you can initiate the device by this particular reset button. So for any electronics device, reset button will do restoring kind of a job. So restoring kind of a job is required, and hence by default all the any electronic device you take, it will have one reset, one clock. Okay, so in this also you have multiple reset pins. When you see multiple reset things, one is for peripheral, one is for interconnect, one is for bus, one is for microcontroller bus, one is for slowest clock. So all it has its own uh, kind of a signaling. So you can change this. When I select this by default, you can see here logic level active high, it is active high reset by default. Depending on the bubble, whether it is there or not, you can make out whether it is active high or not. Now, one more thing is you can fit to window. You can just click on any of the wire. You can see where those signals are getting connected. So your slowest sync clock is getting connected to F clock and also other A clock signals. You can modify these reset connections also. It is not intended to use as it is also. If required, depending on your application, you can modify these reset signals also. Okay. So some of the signals which are not used. So you can connect it to peripheral bus also. And then you can make use of those reset signals also. But provided you should know how to what block it has to be connected. Okay, so that also plays an important role in the microcontroller or microprocessor. So these are the things to be noted. Beyond this, there are many more applications if you go one by one signal. So depending on which you require, you can get into the details of that signal and then you can connect it. Okay, so if I want peripheral A reset, auxiliary reset, then you can check a data sheet related to peripheral AR reset or interconnect AR reset. See which peripheral blocks can be connected to that, and then you can make a connection. Okay, so depending on that, you can go on making the connections. So once the validation is successful, then what you can do is you can go to sources, which module. So this refers now design one is my top module. If you want to make design to top module, you can make that by right clicking it. Design one is a top module. I will create a HDL wrapper. Creating a HDL wrapper means something like you have a chunks of chocolate and you are wrapping up it in a same cover, something like that. So you have multiple blocks here which will generate a binary files. Okay, so the binary bit files will be generated, and that you are wrapping up into a single file, where black box, where you will see as an input, and finally you will get it as an output. Okay, so that is a reason for creating a wrapper, and depending on which code you have written, .v or .vhdl, you will get that particular Verilog or VHDL code. Okay, this will be a reference design for writing structural design for VHDL or Verilog. Okay, so always if it is a block to block interconnection, then it will be a structural kind of a design only. So you will never get to see a behavior of this behavioral description. You have to specify the behavior by writing the C code or by writing the RTL code. So this is all a structural design that you can see. Okay, how the connections are getting enabled. So now, as an embedded system design I am doing, I am not interested in checking out all these things. What I have, the moment wrapper is created by the name followed by wrapper, the wrapper is created, I will select that wrapper and I will generate a bit stream. So of course, you have to go through all these um, steps that is given in a flow navigator. But even if you directly give a generate bitstream, all these steps will be followed automatically. So I will get into generate bitstream. Yes, save the project. Yes, save the project and then say yes. Okay. This may take some time depending upon the complexity of your design. If your design is very complex, the generation of the bitstream will be a little slow. Not only complexity of the design, it also depends upon the system resources that are available. If your system is slow, this process also will be slow. Always the updation of the device can be seen on the right top side. Okay, right top of the page, you can see what's happening with the status. Not only that, you can also get into a TCL console here, and you can see the status of the design runs. Okay, now let it keep running. By meanwhile, I will explain you other things. So now we are okay with our block design. Okay, block design is ready. So I will get into our sources. Maybe this is a design one which I am running now. Okay, so this is a block design wherein I have included BRAM. I am running this particular design. What I can do with this particular design? I simply have included BRAM. BRAM means block RAM, which is a part of FPGA. I have included DDR is there here. Now I can do a data transfer from DDR, which is a memory, to BRAM, which is a memory of FPGA. DDR, which is inside, which is a part of your processing system. BRAM, which is a part of our FPGA. I can send an array of a data from processing system to your PL, programmable logic. I can do that. Okay. Now, here, another thing to be observed here is address editor. You created only a design. I tried to open all these things and show you what is there inside that. Address editor I didn't open. It came up, it was generated, it was seen automatically. Now when you click on this address generator, and if you expand this, you can see the slave that you have connected is BRAM, and it is the type of interface is S_IXC, and this will be the base address. This will be the base address for this particular slave. 0x40000000. This is editable. Who is generating this address? Your AXI interconnect or smart connect has generated this. This is the base address that is being seen. Maximum address is this. This is editable. You can edit this base address to some other base address. But while editing this, you should be very, very careful, because the base addresses should not overlap with other peripheral base addresses. Okay, that is one thing. So it is advisable not to change the base address. Use the same base address. So 400,000, this is the base address and it is a slave segment. So this particular mapping will talk about the networking and the type of the addresses that you have connected to. Okay. Once this is through, what you can do is, I can't do wait for some time. Run synthesis is happening. It may take another 5 minutes, not more than that. We'll wait for some time. Initializing the design, it will take another 5 minutes. So like that, whichever IP you want to add, the other example designs will be shown to you in the afternoon session. Okay, practically on the hardware, it will be shown to you. Like that, how many ever IPs you want, you can just go through this catalog of the IP. Okay, and you can include those IP. You want to include another UART. You want to include, say, binary counter. It is also available as IP. Clocking, you want to design your own clock. That is also there. You don't want to use the default clocks that are given there in the template. So you want to use any of these IPs, it is all available. So you are doing video processing subsystem. You want to make use of that video processing. It is there. Okay. So it is all available as IP. Running place design, running route design. Placing and routing is happening. Running bit stream. So the moment bitstream is successful, if there are no errors in your design and bitstream is successful, you'll get, and on the top right hand, you can see that right bitstream is complete and with a green tick. And you'll get to see bitstream generation successfully completed. Open implemented design, view reports you can do, open hardware manager, and you can run it on the FPGA also. But I want to write now a software C code, correct? To so what I'll do is I will cancel this. I will now export the hardware. Go to file. Okay, export hardware. Go to file, export hardware. So we'll wait for another time. So include bitstream. Okay, then go to next. Finish. So your hardware will be exported to the location where you have created the project. So on the desktop, I created Pink Labs. In that, I created hardware. Inside that hardware, you have project underscore pink, and this is the design underscore wrapper underscore XSA. Okay, so this is a zip file that will be created, which will have the hardware information. XSA means it refers to Xilinx Shell Archive. Xilinx Shell Archive means it will have all the hardware information that you have created. Once that is true, then what I will do is, from the tool itself, you have a provision, go to tool, launch Vitis IDE, or you can open terminal or the icon that is there on the desktop, and you can double click and invoke the Vitis IDE. This Vitis IDE or Vitis IDE is the software platform wherein you can write C++ code, okay, and make your hardware work. So this is the this is the desktop Pink Lab software. I have created a software. In that, I'll create a new folder. I will say lab underscore or software underscore lab. Okay, this is a new name I'll give, and then say open. Okay, launch. We will try to show you the new version of Vitis also, and this will be latest version will be shown in the afternoon also, so that you will get familiar with both the version. Almost the process is same. When you open Vitis ID, here you have this is a flow that you have to follow. Okay, first what you will do is you will create a platform wherein you will include the hardware. Once the platform is created, then I will write the application for that hardware. Correct, no? So that is a procedure that you have to follow. So here, first shown will be create application, but you have to bypass that and create a platform project. So give a name, say DDR to BRAM, or any name you can give, LED blink or whatever, underscore platform. So this is a platform that I am creating. So this will be the template. See, here only they are showing you. You have done a hardware design using a processor. You had dual processor. Then you are creating a platform. In that platform, I will include XSA file. XSA means I told you, no, showed you now. Zip file, hardware file. By choosing a domain. Domain means what? Domain means whether you are doing on a bare metal application or you are using a Linux based application. Okay. So whether you are doing a standalone based or a Linux based application, you have to choose the OS domain. Okay, operating system domain that you have to select. Then after choosing a domain and putting the hardware, then you select system project. System project wherein you will write the application. Okay, this step has to be followed by giving a platform name. Then go to next. Here I will include the XSA file. So from where you will include, wherever you have created and stored it. Pink Labs, hardware, project. This is the XSA that you created. You can see the time also. Just now I have created, and this is in archive file 1.6 MB. Then say open. Here I will get to choose the domain. So the operating system, expand this. You can select Linux domain, standalone or FreeRTOS. Any of the OS you can select. Okay, this will be the domain that or the platform to which the platform will be added. Okay, and then you will have an option of choosing the processor also. This is a dual core processor. No, you can choose any one processor. Either you can choose processor 0 or processor 1. And if you okay, you can select processor 0 or processor 1. Select any one processor. By default, 0 will be selected. I will leave at that point only. Then you have another option here, boot component. Boot component has to be generated. Boot component has to be generated means something like initial, you will have all those uh, booting codes. Booting codes means FSBL. Okay. Like FSBL means first stage bootloader. Means it will tell what all hardware you have selected. Okay. And it will give you the booting information. Booting information means hardware information. What are the default values that you have selected, which memory location you have selected, and what will be the template that has to be worked on. Okay, all those information will be given when you work with this particular, when this booting. Without booting, booting image, you will not be able to successfully run the software code. Correct, no? So you need to have this boot code also that has to be enabled. So generate boot components has to be enabled. Once this is enabled, then say finish. Okay. Once you finish, the platform is created. That usually will appear in a green icon on the white side. Okay. Now, first and foremost, what you have to do is you have to select this green icon. It will show out of date. Out of date means you have to build this configuration. Now, what happens when I build this configuration? You all understand C programming or any C, C++ or any kind of a high level programming you do know, there will be a certain steps that has to be followed. Okay, first thing is building, then compiling. Okay, then finally the code will get converted from uh, human language to machine level language. Okay, that's what your compiler will do. No, after that, finally execution will happen. That is, ELF file will be generated, executable and loadable format. That is what that file will help you to finally help the hardware to execute as per your mapping will happen, and then the execution will happen. So this is your C execution flow, right? The same process has to happen here also. So building has to happen. When I build the configuration, you can observe on the console window. Okay. You can keep observing the console window. When I select this, and there is a hammer icon here on the toolbar menu, you can select the hammer icon or right click and say build. You have an option build project. Both can be done here. Either you can select that or you can build here. Okay. When you build, see here, the make files will be generated. The compilation will happen for all the peripherals, all the customization that you have done while creating a hardware, compilation. So every in a round manner, every peripheral will be compiled depending on whichever you have selected. Okay. By doing this, your by building this platform, your BSP board support package will also get updated. Okay. Now, what is this BSP? Okay. Now, this is what is going to help you on a long term. So now you have selected boot component. So you have Zinc FSBL. Then next is you have selected the operating system, that is standalone, and in that PS Cortex 90. So this is the operating system that you have selected, standalone. In that, this is the processor. Okay, PS7 Cortex 90, and the runtime support will be C, C++ code. Display name will be this QEMU data. Now below that you have something called as board support package. Okay. Now what is this board support package is? It will, when you build it, when you build this, it will add or subtract the libraries. Okay. and it will assign some drivers to the peripheral. Drivers to the peripheral, it will help you to update the drivers. Now, what is this adding the drivers to the peripheral is, suppose, say, I have a laptop, I have a mouse, or I have to turn on the camera. So to turn on the camera, I will have one icon, camera icon on the desktop. Simply what you will do, you will double click and the camera will be turned on. Did you write any code to turn on the camera? Nothing, no, you didn't write anything. So inherently, there is something that is talking to your hardware. What is that something? You have a firmware written. Okay, you have a driver code that is written, which is driving that hardware. Okay, which is driving that hardware, which will tell that hardware to turn on and turn off. Correct, no? Like that kind of codes will be there available for you depending upon what hardware you have configured. Simply now, if I have not included GPIO and if you keep searching for GPIO driver, you may not be able to see it, something like that. So depending on which driver you have allocated, the drivers will be available for you. You can see the driver and use those driver code and then write the logic. So now your job is you will use that template and you will simply write the logic however you want. You will use that template, based on that template only you will write the code and you will write the logic. Logic I know. Now GPIO means what I want to do. I want to blink the LED, so turn on, turn off. Or maybe you want to blink the LED using more control when you only press the push button. So that if else, while, okay, and then for loop. So those simple C codes you have to write and you have to work with the code by using the driver names. That's all. Drivers instance name. Instance name. So simply you cannot use any name and like C program you can you have to assign the variable to that instance which your computer understands. Okay, which your machine understands, which your driver code inbuilt driver code understands. So you have to use those names and you have to write the code. That's all you have to do now. Okay, so how will I find out those names? Okay, I will minimize this. So the moment you build this and get into board support package, here you have drivers. Okay, this is only important for you to write the code now. Okay, so once you are through with the hardware, you have a name of the driver. Since I included BRAM there, BRAM is appearing here. Okay, and what else I have included? GPIO. If you include GPIO, will appear here. If you include timer is there. If you include UART will be there in the first position. Since I included only BRAM is appearing first. Rest all drivers are also there, which is available here. Now what I'll do is, you have a documentation link and you have an example here. You have a documentation link and you have an example here. Okay. So documentation link, if you open, okay, documentation link, if you open, with a proper appropriate internet connection, you will get to know about the documentation, complete detail about that particular peripheral. So BRAM I have connected. What BRAM means? So he will, you can go through this documentation. So driver is intended to be processor independent because it is a memory, it is processor independent, and initialization and configuration should happen for this device. Initialization and configuration by using this name only. So it is a type that is defined with this name. This type is defined with already this name. You have to use this name only. Now I want to understand how the functions has been written for this. If you want to understand how the functions has been written, you have to get into this APIs. Expand this API, you have all functions. Okay, so you want one example only for this, get into this example. Okay, so here he will describe you the overview of XBRAM, BRAM driver. Okay, block memory. which is available. So here init main, init BRAM example is given here with the device ID. So all these configurations, base address, everything will be given here. So you have to refer this and then go through and write the APIs. So you have certain examples here, example code. Okay. So those examples code can also be imported. XRAM, BRAM example. Okay, example.c. If I click on this example, you will have a complete C-based program. So I'll go back here. You will have import example. You can go to this import example. If you expand this, you have XBRAM example. Select this XBRAM example. Interrupt based, without interrupt based. So if you want interrupt based example, you have example for that. This is without interrupt. Then say OK. This is, I'm talking about inbuilt example. If you want to import it, because you don't know how to use the driver, you know only a simple C program, right? So now what I will do is, here you have include files. So this got included here, application. Your platform was there. Now what I did, I went to platform.spr. SPR means software performance report. I went to that. I imported an example. I got this. This is nothing but application. This is an example application. In this example application, if I expand this IC like icon is there, no? If I expand that IC like icon, I will get source. If I expand the source folder, you will have example.c. Example.c. Okay. You have any doubts still here? Please let me know. You have understood how to import? You have any doubts here? Please ask. Can you tell how we will integrate IP in our own RTL code without converting our RTL code to IP block? I will tell. So with so what he is asking is, I want to view that chat again. Anyone else? I will finish this whatever I am explaining process first, and then I will get back to that query. Okay.
Afternoon we are using this Witty software only, right?
Exactly. You will be shown 2-3 demo session afternoon.
Okay.
Now I will give you overview. Afternoon using pink board, we will show you 2 or 3 demo.
Do you install that latest version or like old version?
That's why now I am showing you old version. Latest version, afternoon we will show on the latest version also. Okay.
We want to practice simultaneously when watching this video, na? That's what I am asking. You have
Okay. That process I am not sure. Prince, can you talk about this? When it will be installed for them?
Ma'am, what is the question? Can you repeat?
He is asking about installation of software tools for them on their system.
Okay, installation. If they have any issue, they can raise their concern. Our team will help you to get that installation. But have you
No,
tried with that link? Have you downloaded it? We have provided the link in the agenda itself. If you click on that, if you download it, it is very easy to install actually.
oh, they have not done that process, I think so.
I think
So
they have
that's what
not
he
done
was
that process.
telling. If they can install, they can do along with us, no?
Yeah, they have
So,
not done it.
they have not yet done that. Yeah.
Who was asking, ma'am?
me.
Uh, Ilyas, I think so.
Ilyas, do you have the link of the software?
No, I don't sure about that.
It is shared with the email itself. Agenda is there. In that agenda, there is a software downloading link. If you click on that link, you will be able to download the software. But before that, you have to create the AMD account. That is for free.
Yeah, sir, I have that.
Right, ma'am?
Yes, sir.
Yeah.
Exactly.
Yeah, you have to create an account, AMD account. So after creating that account, if you click on that link, it will pop up to directly to the software downloading page. If you click on that, it will be downloaded, and it is very easy to install. But you have, I think it is 100 GB or 200 GB software. It is.
Oh, 100.
Right.
Yeah, if I am not wrong.
Okay,
Okay.
okay, sir.
Yeah, you please try with that. I hope
No need.
your team lead should have that agenda.
Okay, sir. Okay, sir.
Yeah. And one
And
question
one more thing, if you have older version, let it be, no issues. You can work
yeah,
with
older
older
version is
version
also
also.
fine.
Fine, no problem.
Yeah, no
No
problem.
Thank
issues.
you.
That's the reason I am showing on the older version also, and new version also will be shown. No much difference with respect to Vivado. When it comes to Vitis, little modification is required, that which we will tell you in the afternoon session. Okay.
Okay, ma'am.
So I am
Yes.
showing you now how to write a code template. Okay, maybe for your hackathon you may use say video or some image or something like that. I'm not sure about that, but see, this is the way you can actually include the base file .c program, and then you can keep modifying it. So now I have included this base file, wherein first and foremost that you have to observe is include files. Include files will have always, remember, you will have stdio.h, C code you are writing, that is standard. You will have parameters.h, which is essential for all the codes. Okay. Now what parameters.h will talk about? Okay. What other things has to be included? xbram.h has to be included. This .h file is essential. If I am having a design of GPIO in our code, then I will include xgpio.h. Okay. So depending on which peripheral you are including, you will have that respective .h file that has to be included. Okay. And then select this xparameter.h, control and select this xparameter.h. Press control and select this x parameter. Just keep a cursor on this. You will be redirected to x parameter.h. Otherwise also you can just go through this platform project. In that platform, if you select software expand DDR platform, expand standalone, in that you have BSP include, and inside include you will have all the .h files. Else right click on this parameters.h and you can perform open declaration. All these are the ways wherein you can get into parameters.h. When I include this parameters.h, this parameters.h file will give you the definitions of all the peripherals, irrespective of what you have selected, not selected. It will give you a definition of all the PS component and the PL component that are included. So you cannot go on tracing like this. What you can do is Control F. I want the address for UART. Find. Okay. This will be the base address for the UART. I want address for BRAM. Okay. Go to find. This will be the base address for the UART. So this is the base address for the UART. Correct? No, it is matching. Okay. 40000000 U. Unsigned int. What is 400? 0x. 0x refers to, it is a hexadecimal number. Convenient form of data conversion. convenient form, right? If if the template was in integer, difficult to understand. If it was in binary format, difficult to understand. So hex is the easiest way to convert from binary to hex to binary. 400, yes, it is mapping with my Vivado address editor 40000, so on. That is what the address is, correct? So that is what the address is, and it is mapping. So the base address will be seen as in this, where it will be found base address in X parameters order. And the definition of this X, it is defined as XPAR underscore AXI VRAM control AXI base address. So that is what is specified here. In the C program, if you go through, the C program, it is hung, 1 second. Hung, 1 second. If you go through the C program, okay, anyways, it is hung. We'll give a break for lunch. Okay, and I'll come back and I'll explain you some more details about how to find out this. And then from 3 to 5, we'll have a lab demonstrations. Okay.
Yeah, sure, ma'am. Sure.
Yeah, it is hung. I have to restart. It will take some time. Okay.
Yeah, sure, ma'am. We will have a lunch break. Then we will resume around 2 p.m.
2 p.m. Exactly at 2 p.m. Okay. Thank you.
Yeah.
I'll be online. Yeah.
Yeah. Thank you, ma'am.
Can you hear me?
Yes,
Hello?
ma'am. Yes, ma'am. Can hear you. I'm just making you co-host.
Yeah, please, because I had to re-log in.
Yeah, sure, ma'am. Now you are co-host, ma'am.
Yeah, I'm sharing screen. Hope my screen is visible.
Not yet visible.
Now,
No, ma'am. Not visible. Can participants confirm from their side? From my end, it is not visible.
but I am able to share.
Anyone from the participants, are you able to see ma'am's screen?
No, no, it's not visible.
Yes, sir. We can't see any
Not
screen.
visible. Okay, okay, fine. Ma'am, you can unshare and share it again. Maybe entire screen you can share.
Okay. Now,
No, ma'am.
what happened? Visible, it seems. Somebody has messaged.
Somebody is
Yes, ma'am.
messaging.
It is visible. Yes, ma'am. You can go to other screen right now.
Check now.
Yes, ma'am. We can see that.
Yeah. Thank you. So we'll resume back. So this is, I was talking about how to come up with the code. So this is how you can come up with the code. Here, so first thing is include files, and then finally you can define the devices that you are using. So this will be user defined name, finally followed by the device ID name, which was, we got it from parameters.h. Then function prototypes. Okay. Every time you call the function, you want to configure or you want to execute anything, you want to initialize, you will get an template here. Suppose, for example, xbram write reg is there. So what I'll do is I will simply, I know the now I know the format of driver functions, how it has to be written. Always the capital letters followed by small letter with the same name, but with the prefix X, Xilinx driver. So now it is AMD. So you can type XBRAM, then select control and scroll this one, um, the keyboard button, spacebar menu. Okay, control plus spacebar menu. If you press, no, you'll get to see the template options. What is it that you want to use? Okay, so self test. So you'll get various templates here. Config initialize. So what is that you want to configure? Lookup config. Now, what all I should use, that I will get to know from the function file, which we have seen already, right? From that function file, I will be able to identify. So you can perform configuration. If you want to use it as in, you can use it as in. If you want to use it as out, you can use it as out. Okay, you want to use it as a read reg. For example, I will select this. Then you will get the entire detail, what parameters has to be passed inside this function. So base address followed by reg offset. So base address, you all know the base address. Okay. So this is the base address that we have to put, which was declared initially. Okay. So this was the base address that we have to put, followed by effective address or whatever the template was shown. So you can just go on including the functions in that particular manner. Suppose if you are using GPIO, so GPIO, XGPIO, you should put XG. Then follow control and spacebar menu. So what you want to do, whether I want to write into that or read into that or set the direction. Suppose if you want to set the direction of the LED, then instance pointer, bank name and direction. So you have to assign some instance pointer. That instance pointer will be pointing to the XBRAM config. So how to define the instance pointer? This is the way. You can define this is the instance pointer. So XBRAM, you are calling it as BRAM. Some instance pointer name has to be given. You will not be using the same names. So this is how you can use the template that is usually given. So the same way XBRAM write reg is also used here, effective register followed by the offset register. Then there are other things also that is included. Okay, this is a self-test example, whether it is success or failed. So if I have given any address, then success, otherwise it will fail. So once the program has been written, then you can select this IC kind of a design application, then you can say build. Okay. So only when build is successful, then you will get to see the ELF file. Okay. Otherwise, you can see the build progress on the extreme top bottom right corner. So build is finished without any error. If there are any problems, you can check into this problem. As of now, there is no problem. If there was a problem, description would have been given and you could have used it. So once build is successful, you will get .elf file. Okay, cedd xbram, whatever name is given for that xbram underscore example.c. So elf file will be created, and this is the segmentation, text data BSS. Okay, based on the code that you have written, data segmentation will happen as per our C program only. Once it is successful, right click on this. You can go to run as launch on hardware if the hardware is there. If hardware is not there, and if you are into a Linux system, Ubuntu system, then you will have a facility to check on the software emulator. Okay, you can start and check on the software emulator. On the emulation console, you can see only the print messages, through which we'll come to know that okay, whether the code is successful or not. Okay, then here as of now there are no such print messages. We can put some print messages and check it. Go to Vitis. You have an option of here start or stop emulator. You can stop emulator. It is running. You can stop the emulator. Launch process was successful. Okay, so emulation ran successfully. So this is only a test code that you can do. After some time, shortly we will be showing it on the hardware by running the actual demo code. Then this is one way. The other way is I want to now visualize what is happening inside the memory window. Correct, no? So if you want to visualize what is happening inside a memory window, right click on this, debug as launch on hardware you are supposed to do. If you have a hardware. If you don't have a hardware, you cannot check. Debug as launch on software emulator only I will do as of now. Okay. Start emulator and debug. So when you perform debug option, then you will be able to see the memory window, visualize the memory window. Otherwise, you will not be able to visualize the memory window. So here you have already got a memory window because maybe I have already opened it. You can go to Windows. If you are not able to see any of these windows, you will have memory module here. So you can click on this memory, this visualization will come. Now I know the memory address, right? So I will go to add monitor. I will type the memory address 0x4. This is the memory of the VRAM. Then I'll say okay. So if you want to write anything into this, you can just expand this. You will be able to write and read as well. Okay. But that depends on how I have written the code. If I have written as per the, this is only a test code. You will not be able to write now. So depending on that code, you will be able to write and read from the memory window. This is a memory. And we all understand that this is ARM, correct? No, ARM processor. So here you can see that this particular location is 4 followed by 7 zeros. Next location will start from 4004. That means 4000 to 4000003. It is same memory location because it is 32-bit. 32-bit means memory is visualized as 4 row is equal to 1 address. Okay, 4 row is equal to 1 address. It is called as conjoined architecture. It is a conjoined architecture. 4 row is equal to 1 memory location. So whether you write in 40000, 4000001, 2, 3, it is all same. Okay. If you try to write 3 here, and if you write to 3 again in 40001, overwriting will happen. So you have to write from next new value, you should write from 40004. This is how the memory template is. Okay. This is about memory window. How many ever memory module you want to add, you can add and you can check the output. Okay. This is about memory window. There are other windows available like you have here register windows. You can visualize the registers that are associated with the ARM processors. Okay. All these are the registers associated with the ARM processor. Once you have written this, you can debug this. How to debug? So you have an option here, resume. Directly you can resume, okay? Or you can step into step over, okay? You can add a breakpoint and you can perform step over. Step into, if you do, it will get into all the .h file. So option is you can get a step over the code. So whatever you are visualizing now is a disassembly window. That is a assembly language code, low level language code. Okay. You had written a code in C template, got converted into assembly language .s file, and finally you got a ELF file. So this is what is called as a disassembly window. Okay. You want to come out of this window, you have an option here, terminate, disconnect. So disconnect this, you will become out of that particular window. So go back to the design. You will be back to the design. This is how you are supposed to work with as a debug mode and non run as hardware, and another one is debug as hardware, launch on hardware. Okay, you can check this. Now this particular application, I took it from software performance report. You can do another way. Another way is I can go to file, create new application project. You want to write your own C code. I can go to application project, then go to next. Go to next. Here you can again give a name, DDR underscore BRAM underscore app. This name I will give. So the selected processor is PS7 Cortex 90. Go to next. Next. Hello World. Okay, Hello World is the application, then finish. You can do this also. Okay. So now when I select Hello World is a template I selected. Like that you have many more template. When I selected Hello World template, when you expand this, you have hello world.c. See here, this is a simple C code that is written. already written for you from the template. So this will print hello world successfully ran hello world application. Okay. So if you want to run this application, build this. Already built. If it is already built, go to run as launch on software. No. Software emulator. Okay, some issue. I'm just restarting the IDE. It's not working as intended. That's PPTs will not be shared. Older version will do. How to integrate your own RTL code without converting to IP block, I will show. So hello world.c. First I'll build this. Yeah. So here we can get to see the print messages. Hello world successfully ran hello world application. So this is how it works. Okay. Embedded system design, how it works. So if you want to write your own application, I don't want to choose anything from the template, neither from the driver, that is also possible. How it is possible? What you can do is you can go to file, new, application project, go to next. So I'll write new underscore program is the name I have given. Go to next. So here what I'll do is I will select empty application with C. When I select empty application with C, if you expand this source, here you will not have any .c file. What you can do is you can include the .c file. How? Go to new program or source, right click, new file. Okay. Whatever file name you give, no, say for example, hello world. Okay. I will write .c. .c should be the suffix, then say finish. That template has been included here and this will be empty. You will not have a template which looks similar to this. Okay. You will not see all these things. Now the same code, you can, hello world, I will put it here. Okay. Save this. Platform.h will give you an error because you are writing absolutely a new code which is not calling any dependent codes. So I am just commenting it out. Save this. Still, it is because init platform. It is trying to initialize the platform, which You have not called at all. So again printf. So again you right click, run as, launch on software emulator. Restart emulator, because already it is still running. You have to restart the emulator and then build this. So hello world successfully ran hello world application. So this is how you have to work with. Now suppose somebody is interested in adding a different operating system, then what you can do? So every time what you should do is you should go to platform.spr under platform that you have created. Go to platform.spr. Here, what I will do is you can add the domain here. See, you can see on green color highlighted one now, you can add the domain. So I will use another processor also you can use. You can use new operating system also. Both are possible. So I will give new underscore platform. Some name I'll give. Okay. Here, the operating system is standalone. You can change it to Linux. If you change it to Linux, it may require some BIF file, dependency files. If you want to work with another processor, that is also possible. Standalone. Till now, you have selected a 9_0. You can select another processor here. You can select another processor here and then say it is 32-bit architecture only, no? So you can say okay. The moment you select another processor, it will show out of date. Again, you have to rebuild this. Now you are using another processor, 2 processors you are using. Okay. Now you want to create another application using new processor. You can create that. So what you can do is one processor is doing one work, another processor is, suppose one processor will give a command, another processor will blink the LED, something like that. You can do that. Inter-process communication. Okay. Inter-process communication is also possible. Now I will go to file, create new application project. Okay. And I'll go to next. So here, this was main hardware did not change. Only now is I am creating multiple application using multiple cores. That's all. Multiple CPUs. Then go to next. Here I will get an option here. See, this was an older processor. Now I have added one more domain which included the new processor. I will select new processor. I'll give new name. Hello world underscore new underscore app. Okay. Then I'll say next. Next. So you'll get a new application template. You can select new application template. So hello world. Then say finish. So now I created another processor with same, of course, same code. Hello world only. So I'm doing that. Now while running the codes, what you are supposed to do now? You have a multiple application. You can select any one of the application. Okay. Select any one of the application. Go to run as run configurations. Go to run as run configuration. Here you have an option. Go to application. Select this one. But still I have not built it, right? So what you can do is don't say cancel. So I will select this, build this, because I didn't build this. I have to build this. Both I will build once again, okay, simply. Both I have built. Select this application, run as, launch on, run configurations. Now go to application. You can select both the application. Select both the application and then say apply. See, both the L files have been added. And then you can perform run operation on the hardware. It works. Okay. This is how you can work multiple processors also you can execute. Okay. Multiple processors also you can execute. You got now output. See, twice I got hello world successfully ran hello world application and hello world. So you can do like this also. Okay, all these are the options, various options that are available under Vitis terminal. Okay, now there's another option here. I told you can load the image onto a SD card and you can put it on the hardware and you can make your hardware work. But I want image, correct? No? So if you want image, what you should do is you should select the application that you are intended to run, right click, create boot image you should do. Okay, right click, create boot image, or go to Vitis. Here also you have an option, create boot image, Zinc and Zinc Ultra Scale. All the devices options will be given here. So there one more, whether you are creating for Zinc using Zinc or other devices, you have to select here. So by default, all these things will be selected for you. If it is not selected, from the project path, okay, from the project where you have created the project, no, from there you have to select these BIF path, add here, and then here you have to add the boot image partitions. What are the boot image partition? One is your application.elf file, your boot image.elf file, okay, and hardware bit file. These three are required. Okay, so those three has to be included here. One is your application elf file, another one is your hardware bit file, another one is your boot fsbl.elf file. All these things will be under the partition, available as a partition under the project path that you have created. Okay, select that, create image. Okay, once you say create image, see here you got a message, boot image generated successfully. Where this boot image will be? Under the project path, okay, that you have selected. So maybe I don't know where is the location, we'll just check. Okay, here underscore system underscore IDE. Okay, scripts. Okay, 1 minute. For which one I generated? Hello world I generated, no? I opened some project. This path is hello underscore new underscore project underscore new. Here. Here. Project underscore new boot image. This is what boot.bin is. This file you are supposed to copy and put it in SD card. Okay. And load it in SD card and you have to boot via SD card mode. So that is what you are supposed to do. Okay. Next is somebody asked me if I want to write my own RTL code, how to write. So what you should do is you should go to your block design. This is Hung now. 1 second. So here I'll what I'll do is I'll open this only. Okay, this is open. Now here I will select block design. Suppose I will write a very simple code, okay? For this a hardware design, I can include RTL also. How? I'll go to sources or add sources I will go, or here also you can go. Add sources, add or create a design source, go to next, okay? Now here I will, if already you have a RTL code, add file. Otherwise I'll create file, okay? I will say and underscore test, okay? I'll give this name, Verilog code, okay? And then I'll say finish. So I will not give inputs here, directly I will write it as a RTL code. Now go to source, that will be included here, right? So this and dot, this is included. Here I will try to write the code. So AND gate, I will need input A comma B, 2 input AND gate, okay? Then output Y, okay? I'll include this end module. I think there should be no error. Yeah, no error. Then save this, okay? Save this. Now I want to include this as a part of my design. Design 2 I will remove the project, okay? Now this one, I want to include it in my RTL design. So what I will do is, for BRAM, I cannot include, no? So what I'll do is I'll include one Axide GPIO. I'll perform run connection automation. Before that, you want to configure this. I will custom this as LEDs, okay? And then say okay. Then run connection automation I'll do. I'll say okay, okay, okay. I'll do this, perform this. Now I will remove this pin, delete this also. What I will do is, this AND gate is there, no? Select this, drop down here. With this is, I am dropping down and creating this without IP creation. This is RTL code. Just I selected this, I have dropped it here. So it looks something like this, RTL code. Now this output Y, I'll give it to this, further you have to customize, okay? Give it as an input to this GPIO, okay? And this A and B, I don't want to give it as an input. You can drag and drop here also like this. I don't want to give these two as an input to any of the blocks. Simply you want to give external signal, that is also possible. So I will select this and I will right click and I will say make external. Similarly, I'll select this, right click, I'll say make external. This you want to rename, you can rename also, okay? So I will select this, you will get to see the properties here. I will rename this as switch underscore 1 or 0, okay? Similarly, I will rename this also switch underscore 1. This is also possible, okay? So these two are the input, that is, I will configure switch as 0001 1011. Apparently your gate logic output, whether it is 000, will be fed as an input. All LEDs will be off. 0111 is fed as an input to this. Something like that. I have to revamp the code again. C program I have to revamp. Then accordingly you can use this also without using it as a IP. Then I will verify, validate. But one more problem is here. Okay, okay, fine. One more issue is, for this, all these are inbuilt board properties there. Here, it is all board level. All these addresses are understood at board level, and you get a mapping, routing and placement of the design will happen automatically. But this is, you have written a code. For this, you have to give a pin constraining has to be done. So you have to add a constraint file. So you have to look for a pink Z2 constraint file, and depending on whether you are using it as a switch or a LED or whatever push button, depending on that, you have to include a constraint file and then you have to generate a bit stream. Am I correct? This is what was asked for you. Is it clear for you how to add? This is what you asked, right?
Yes, ma'am.
Govardhan Reddy had asked me this. This is what you asked, no? Govardhan? Understood, no? The only thing is now you have to add the constraint file. Constraining has to be done. Then you will be able to check with the design. Okay? Clear with this? Now, if you want to create IP, that will be done. Custom creation of the IP is done tomorrow. You can check how to create a custom design. Now, one more option is entire design. Also, you can package it as a IP. This entire design, once you are through, no, what you can do is you can go to tool, create and package new IP you can do. Okay, you can go to next, create new AXI for or without AXI, package your current project. Okay, package your current project, go to next. Okay, okay. Why means this folder, it will not, home folder it is showing. I have to choose some other location. That's why it is. Go to desktop. Here, Pink Labs. Okay, I will select this location and I will say next. See, finish. Entire project, it's also you can package it as a IP. Now I am packaging entire project as a IP. That is also possible. Okay, done. But there was one critical, because I didn't give any constraining, no, that will give me the error. So I will now check on the desktop. So this is what is packaged as a new IP with the TCL script. Okay. So that way you can create your own IP also. Okay. User IP. Okay. Still I have not packaged. This window will appear for you. Identification, compatibility. To which all family you want to make it compatible. Add family explicitly. So I want to make it compatible for other families also. You can do that. Okay. And then file groups. Merge changes with the file groups. Okay, customization GUI. This is how it looks like. Okay, so review and package your IP, package IP. Once you package your IP, you can go back, desktop. Why
It
it
is
is
going
not
to be there in the
packaging?
IP
Finished.
catalog.
Design underscore one underscore wrapper. The location I'm forgetting. So it will be because of the critical warning, it is not able to package. Okay, so merge changes, everything I have to do, then it will work. Okay, so root directory will be home, this one only. So here it will be packaged. Okay, it should be packaged. This TCL script is, this is, that's how you will be able to package the IP also. Okay, so it's not. Okay, tomorrow anyways they will show you the packaging. Now this is one option. Okay, then you have to add the constraint file. Constraining has to be done, and then you will be able to look into this. So final, another 15 minutes conclusion. After that, okay. Okay. Now after that, this is about overview of all the software tools that I've shown you. So finally, you'll be using this lab. First, you look into the requirement, specifications, system design. Okay, software and hardware partitioning has to be done. Hardware development you do, as I shown, using Vivado. You can do the software development using Vitis, and you can integrate and test it on the hardware. And this will be the pink board that you are using. Okay. So if you look into this pink board, this will be your SD card exactly backside below the board. Okay, you can place the SD card. These are the buttons for programming and system reset. You have two slide switches. This is user defined. And then you have LEDs. These are the LEDs, RGB LEDs. You have four push buttons. Okay, four push buttons. Above that, you can see the user defined LEDs. Okay, user defined LEDs. Then you have, this is the jumper mode for boot mode setting. So if you can read here actually whether you want to work with it as a JTAG mode, whether you want to work with it as a SD card mode, or whether you want to work with it as a QSPI mode. There are three boot mode settings. So if you place the jumper at the extreme two end, it will be for JTAG mode. Okay, this is HDMI in, HDMI out. You can connect your headphone and mic to this particular port. Ethernet. So as I mentioned, Ethernet based connection can be connected here. And then buttons for programming and reset. So this is how you can make use of this particular pink board. For hardware design, use Vivado. For software design, use Vitis IDE. And this will be the memory mapping for Cortex A9 processor. Okay. So this is how you can use. So be online. Prince, you're there?
Yes, ma'am. Hello. Am I audible, ma'am? Hello. 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 Can someone confirm? Am I audible?
Yes, sir.
Okay, okay. Ma'am, are you there?
I am there now from 3 onwards.
Yeah.
Manjunath.
Okay.
He is senior application engineer. He will be giving a demo
Okay,
session.
ma'am.
So I will just confirm at what time he will join.
Okay, sure,
Okay.
ma'am. Yeah, sure, sure. In the meantime, participants, if they have any doubts, they can ask their doubts to ma'am. And in the meantime, Manjunath sir will join.
And you have to, yes, Manjunath sir will be joining. Yeah.
Yes, ma'am. You were saying something.
You have to make him co-host, I feel.
Yeah, I will do that. Once he will be joining, then just let me know. I will make Manjunath sir co-host.
Sure.
Hello. You have any other doubts? You can put messages on chat. You can hear me, right?
Yes, ma'am. You are audible, ma'am.
Yeah. Now,
Participate.
Professor Manjunath has joined. Prince.
Okay. Yes, ma'am. I will make co-host.
So, you can make him co-host.
Manjuna sir, now you are co-host. You can share your screen.
Yeah, thank you, Chipin team.
Thank you, sir.
Can anybody confirm me that the screen is visible and I'm audible?
Yes, sir. You are audible. Screen is also visible, sir.
Okay, so I think Madam has explained today entire flow of Vivadvo to till Vitis flow, I guess. So I'll be demonstrating you the few of the demo, which is on embedded design flow. Uh, uh, taking through the as a walkthrough for embedded application development, how you can do it on our Ping Z2 boards. Not only on Ping Z2 board, any of the Xilinx FPGA boards, so that you can be aware how the flow will look. And maybe I think one of the example Madam has shown you regarding how you can develop your own applications using any of the FPGA hardwares are available. So to get into today's agenda, so we'll understand the prerequisite, what are the prerequisites are required, and what are the demo contents and its outcomes, and then we will discuss about the Vivado design flow. So I'll not go in detail, but I'll just tell you the what are the steps you need to be followed here, and then we will walk through the VT's design flow, and then how we can access the peripherals. So we'll understand that. So what are the peripherals are available on PS side or PL side, so that we will understand, and how we can access if PS side peripherals are not sufficient, how we can go ahead with the PL side peripherals. That is one thing we will see, and then we will go ahead with the hardware demonstration. So as a prerequisite, what are the things are required? So kindly make a note if you wanted. So as a prerequisite, one is any of the FPGA hardware board. So we are in this demonstration, I am taking Ping Z2 board. That is essential. So this board will be dual power, which will be either using USB power or using an external power also. I think Madam is explaining you regarding the board contents. So might be you are aware where you can choose a USB power. There will be a jumper provided. Make sure that you have to follow the data sheet provided by a particular vendor. So for Zinc Ping Z2 only, we'll have some user manuals. You need to refer the user manuals to understand the board properly. That is one aspect. So if now since your Ping Z2 board works with USB powered, so we doesn't require any external power supply for the hardware. So Ping Z2 board with the one USB cable, that too micro USB cable is sufficient for the usage. So the next is we essentially required two software tools. So one is Vivado. I think from yesterday, I think you got to know how you can design your like create your own source code or add custom IPs, and then you build smart designs, and then how you can simulate it, and then how you can take it further for your own interpretation. That entire thing you have seen in the Vivado software tool. I think today's, I think a few, one of the example you might have seen how we can gather the bit file and converting the same and then exporting it to an embedded application where you can access the peripherals on the SOC portion. So that we will see it with his software tool. And apart from that, what are the other tool we use? It is a serial terminal. So serial terminal is basically either any third-party vendors, like you can use Teraterm or Putty or any other serial terminal as well. Apart from that, Xilinx also provides a serial terminal for the users to use it within the VITIS environment. Okay, so you can rely upon the existing terminal as well. That is one more thing. These are the prerequisite for the any implementation we do with uh, Vivado or VITIS. We require these many prerequisites for ping Z2 board. So coming to the demo contents, so what are the demos we are going to see? So we will see the demo one, how to print a message on the terminal. I think this portion, I think Madam is telling that she has covered a portion of it. So maybe I'll not just get into in detail, but only with some code I'm going to execute, and then you can see that in the terminal printing. So that is one first demo we will see. And demo 2 is how do we send any data through UART, a byte of information. Okay, so whenever whatever the keys, I'll press it in the keyboard, that has to be displayed back. Okay, so that we will see it. So send and receive a byte of a data using UART, that one more example we will see. And demo 3 will be your GPIO access. So whenever we concentrate on a GPIOs, it will be both sides. So PS side also as well as PL side. But on ping Z2, there is no PS side GPIO to access. So what we do is here, we are going to access the PL side, that is programmable logic side, that is entire fabric where the FPGAs are there, pure FPGA portion where the LEDs are assigned. So we were going to access those LEDs by means of an AXI interface. And then how we can toggle those LEDs. So we have four quad, that is quad LED we have on the board, which is defined for user application. And coming to the last demo, we will see actions performed. Like suppose I have a push buttons or a dip switch, how we can access the push buttons, and then based on that we actuate our LEDs. So it is a demo 4. What are the outcome? So how we can like develop our embedded applications on the VITIS platform. That is one thing. That is one of the outcome. The other outcome is how do we configure the peripherals for internal or external use. That we will see it. So moving further, getting into the design flow. The first, there are two design flow we have to understand here whenever we are building any embedded application. One is Vivado design flow. So what we do with Vivado design flow is we will configure our processing system. So we have Zinc processing system, which is basically an SoC. Um, and we add upon few of the processing system peripherals. That is one thing. And apart from that, how do we access the programmable logics? So we the portion of the FPGA, how we can access through Zinc processing system through the peripheral interfaces. So what are the say like peripherals we are interested here? In our demonstration, we will take it UART or GPIO and with AXI peripheral interface. So what are the steps that we need to follow here? So first thing, we create one project, and then in the project we create a block design. Okay, just make a note of these things so that it will help you in your embedded application. First we create the device specific project and then create a block design, and we are going to add the inbuilt applications in terms of an IPs, intellectual properties. So those dedicated IPs we will tell, we are going to add those in our block design, and then we are going to add the peripherals with port connections pins. So we providedly, if you access the uh, programmable logic side peripherals, so we required a constraints. So we have to constrain by giving already existing constraint, or you can follow the XTC file, so which is specified by the AMD, which is Xilinx design constraints we call it as, which comes up with an IO constraint files for specific to like specific to the board. we'll have one XTCs. For ping set 2 only, we have one of the master XTC. So there you can access to those constraint files and then you can add it. That is one part of it. Then what we will do is we will validate the design after adding all these IPs and doing all the constraints. Then we validate the design and then we create a STL wrapper. So STL wrapper is basically you are going to have a different IP components. So those IP components will have a different file structures. So you need to comprise together to form a one top level module. So that is basically your STL wrapper. So you're going to make that STL wrapper, and then after that, so we will follow the steps of same synthesis, implementation, and then finally bitstream. So since we have to deal with embedded applications, we will skip these portions. Directly we'll give bitstream generation, but inherently your Vivada tool will follow with synthesis and the implementation portion. And finally, when the bitstream is ready, then taking that bitstream, what we will do is we are going to convert into an archive file. So which is basically a Xilinx shell archive file. So once we generate this archive file is acts like a base element for your embedded application. Please remember, without an archive file, you are not going to build any of the embedded applications. So make sure that whenever you concentrate on any SOC implementations on your FPGAs, you must have this archive file. So what are the steps to be followed in VTs? Now just we'll get into that. So so we will take this archive file, whatever the Xilinx shell archive file we have, we are going to take that and then we create a platform. Okay, so the platform is basically is giving you an information about what are the peripherals configured and what are the IOs available, and there whatever I think in the last concept what Madam has covered is regarding the memory map, right? So all this structure, like each and every peripheral will have a dedicated address for that. So that address are specified in your platform basically. So that is one thing. And any structures where you are configured any variable, so that variable will be having a certain set of files. So either it may be having a header file, so or a source code as well along with that. So we are supposed to understand what are the header files we have to add it to our applications and what are the source code we have to add it. Okay, so that is a portion of your embedded application, so that all the informations are available in your platform. So once the platform is ready, you are going to create your own block. So in the apart from this, in platform, what else is containing? So platform is basically containing one more information where you have a access to the entire structure of your course available on your Zinc processing system. So we have a dual core processor here, so which is basically we have PS0 and PS1. So we have these two dual cores. So in between these two cores you can select in the platform. So apart from what I told, the source file and header and the your memory map, I can say, for a particular variable peripheral. So all these things, apart from this, we have a course also, specified course. So these cores are standalone as of now, and then there are certain Linux or RTOS based implementation also. So that will be taking care later part. Now, as of for you to understand, first understand what platform consists of. Platform consists of all the header files and source files pertaining to a particular peripheral and even the board design files. So we have something called as a BSP, board support packages, which will be having all this information, and then we'll have a specified course for that. So coming to the next step. So once we create a platform, okay, next is a application project we are going to create it, which is user defined file. So we are going to create an application project linking to our platform. So without linking your application to platform, you're not going to access any of the source code or the files associated to your platform. So if you are building standalone application without a platform, it is nowhere it is going to take your the settings or the peripheral access from your Vivado. Okay, so without a platform, we are not going to building any application project. So make sure that you have a proper platform, and then you're linking the application project to the existing platform. So that is the main objective. So that is a second step we follow. As a third step, we add our source code. Example of source code, any peripheral if you take. So one way you start up with understanding its behavior. So it may be I2C, SPI, or UART, or any peripheral in that sense. So you are going to take that peripheral. First, you refer to the protocol-wise analysis. So you understand what are the protocols available, and what are the steps to be taken. So initially, we'll start with initialization of any of the peripheral, and then we are setting a direction of it, whether you wanted it for an input or output or any other applications. So specified application you specify. After that, you are going to map the application. So if it is UART, then you set a baud rate, peripheral rate, other things, right? So and then what we'll do is you are going to do the transmission and reception portion. So that is what you add it in your source file. So you're going to customize not only the customization. So we have everything available, readily available in your platform. So when you create an application project linking to a platform, so all those header files and C files are available. You can directly go to that. You need not to initialize multiple times. So you take the constructs used in your header files and then add it in your source file, so that the less time you will take it for your application building. So that is third step. So after this, whatever the platform and then application you created, you have to compile it and then make sure that it is error free. If any point of time any of the peripheral, like having applications or platform is having any errors, so that will be displayed in the transcript or the console window. And then finally what we do is, once the compilation is error free, then we directly do the programming to the hardware. So basically the hardware what we have taken is ping Z2. So these are the steps that will be followed for the demonstration. So coming to how we can access the peripheral. So there are two portions in the FPGA. One is PL, another one is PS. Okay. So before I get into the demonstration, please understand PL is entirely your pure FPGA. Okay, so which is having a regular structure of your CLBs. So there are certain peripherals associated to PL side. So PL side, so there are GPIOs are linking. There are certain bare metal application. There will be certain external bus interfaces also they have given in the board. And apart from that, you can use only the pure FPGA portions which is connected. But whereas when we concentrate on the processing system, using processing systems, so there are dedicated pins available for us to use it. So what one of the example what I have taken is the processing systems UART directly from the SOC portions. So only PS side UART I am going to use it for one of the application. And another application we will take PL side GPIO. Now you can see here, observe. So we have the peripheral present in PL, which is GPIO. In order to access this GPIO, so what I'll do is I'll just cannot directly go and then take the PL peripheral just like that. So we required an interface. What are the interface we have is, we have something called as a bus architecture, AMBA bus architecture, which is basically advanced microcontroller bus architecture. So this will be having AHB and APB. Okay, so your AHB, your for high speed applications and high performance bus. So the extension of the AHB is your AXI. So we are going to access the AXI. So any peripheral you are accessing it to the PL side from PS side. So we have to incorporate a AXI interface. So that is one more demonstrations, and then we will go ahead with the same. I think you understood now what is only PL side and what is PS side peripheral, and then how do we access PL side from PS side. So one more objective I can tell you, why we need to access the PL region, right? That is one question you might get it. So just understand in SOC portion, let us take only we have two GPIOs, two LEDs are present in PS side. So I wanted more, right? So it is like your PL, your programmable logic, will be having the flexibility that any pin, okay, which is free to use, can be configured as an GPIO or any other peripheral. So that is why we call our FPGAs are reconfigurable. Okay, so whereas in case of a PS, we cannot have any reconfigurability at all, because if it is a dedicated pin, you have, must and should have to use that dedicated pin. So that is the idea behind why we need to go for PL side GPIO through AXI interface. I hope I am clear to all. So any questions now, just before we get into the actual demo? So if you're having any questions, please do let me know so that I'll clarify if you have any doubts.
Yeah, if participants have any doubts before the demo, they can clarify their doubts. And then we will move to the demo part. No questions, sir, in the chat box also. You can
Yes.
proceed, sir.
Yes, I can go ahead. Yeah. So one of the demo, the first demo is printing a message on the terminal. So I think first two demos what I have going to show you is based on UART only. So what I'll do is I'll configure my Vivado flow for one application. So and then I'm going to have two different application linking to one platform. So that I'm going to do it. So what I'll do is, so I'll just show you the normal demonstration, and then what are the settings you can do it. Once after that, so what I'll do is I'll readily available uh, file. So I have this empty folder. I'm going to access this now. So I'm going to use Vivado 2024.1. So I think the latest release is 2024.2. So that you can use it. Instead of this, if you have any other versions also 2023, 2022, so you are free to use those tool as well. So the structure is almost the same, so there is no difference in that. So I'll just create a project. I'll just give the path of the location. So I'll just take project 1, or I can say design 1. I'll tell design 1. Let's take this. So RTL project. Next. It's the same step as what you have followed in Vivado earlier. Okay. So I'm not doing anything special. So one is you have to select the PingZ2 board. So when you want to download these packages, no, so you have to make sure this you refresh the catalog if it is not available. Okay, just only type in the search option here, ping, and then if it is not available, you refresh it. Then obviously it will going to take the catalog. Your firmware catalog will be get updated. So then you can install this. So uh, there are many packages will be there pertaining to this board that will be get added. Otherwise, what we have to do is the other way around is you can program the device by giving the part number, specified part number, which is used in your specific board. So I'll just finish this. So I'm creating a project. The creation is done. I was talking about your XTC file and all, right? So you have the website of the board from where you have got it. So it is from TVL. So just one more manufacturer who will provide a ping set-top port. So basically they use our Xilinx boards, and then they will customize the bombs, and then they are going to come up with the board setup. So that is why the different vendor you can find it here. So now what I'll do is I'll just directly go to the block design creation. So this is my IP canvas. So what you are seeing here, this is a diagram window. So you have the you are adding your own IPs, then you can have to give the path, repository path, and then you can customize and then do it. Now what I'm doing is already existing IPs I'm going to take. I'll just type Zinc processing system. I'll just take that Zinc processing system. Now what is there in the Zinc processing system? Just we'll walk through with that. So you can find these many peripherals: SPI, two SPIs, two I2C, two CAN, two UART lines, one GPIO, but it is not dedicatedly given, but they have given it for the other use. And we have SD card use, two SD card, and then you have two USB, two Ethernet ports support. But on the board you can find only one Ethernet board support. And then we have SRAM, NOR based flash, or NAND based, or quad SPI. So basically a memory interface, which is basically acting like an EEPROM. So apart from that, we have timing SMC timing calculations internally. So we have clock generation unit, and we have 32 bits GPAXI master port, and then we have slave ports. So for high performance AXI, we have a slave port. Those are the things. And then we have DDR2 or 3 support with LPDDR2 as well. We have support low power DDR dual data or double data rate access, memory access. That is one thing. And we have AXI ACP, and then we have a watchdog timer, we have a timer counter. So other than that, we have a dedicated IOs and multiplexer units. So in the Zinc block diagram, you can find out all these things. So coming to configuration, so whatever we have seen in the Zinc block, which is available here. So you have the baud rate setting for the UART. You can set it here if you want. So what baud rate you want to operate at. And then you have slave interface. You have DMA controller. We have PSPL cross trigger option. So peripheral IOs. So you can see whenever we select any of the peripheral dedicated, suppose I'll select this, the NAND flash will be enabled like that. So that peripheral, you are going to access it from this window. So you configure your PS, that is entirely a processing system. Whichever you want, you can use it. So whenever you enable, so that dedicated IOs will be getting highlighted. Okay, so you can see UART1 is getting highlighted here, so like that. So I'll just not do anything as of now. I'll just show you the other method around. And coming to the next one's MIO configuration, we have memory interface. We have quad SPA, SRAM or NOR based or NAND based flash memory usage. We have IO peripherals and application processor unit. That is, I told you, right? Timer and watchdog timer. So test and debug trace ports we have. So the main feature is that how do you trace the path and where the hardware is causing the error. All those things you can rectify. Okay, so not with the hardware, with respect to the tool wise, you can find out what are the um, uh, which portion of debug unit are not working, that you can recollect and then reconfigure it. So that is the one of the feature. And then we have processor clock, so which the CPU of zinc processing systems are operating at 666 megahertz. So with the DDR PLL will be operating at 533 megahertz. So basically, I can say your PingZ2 board, which is having an internal fabric clock as 125 megahertz, and SoC portion is acting like 666 megahertz for the usage. So we have IO peripheral clocks apart from that. And what are the speed we have? So we have Ethernet, which will be operating at tri mode, I can say. So tri mode in the sense 10 mbps, 100 mbps, and 1000 mbps, or 1000 in the sense 1 gbps it can operate. So those are the things. And timer system, other things, configurations. And then we have DDR configuration, DDR memory. Okay, memory already there is a micron, I think. Micron or Marvel ICs are already been there on the board, FPGA board, so which is having 32-bit interface. So the operating frequency is 533 for DDR memory, that we have seen it. So those things. And then we have SMC timing calculation also, that also it is there. And then if you want any interrupts to be used in your design, so you can enable this. So this is regarding overview of your processing system. So what I'll do is, as a prerequisite, so I'm not going to use any of the clock. So what I'll do is this fabric clock and your AXI clock I am going to join. Okay. Now what I'll do is I'll just click on this run block automation. I'll just click on OK. So now I'll just reopen this. What has happened now? So I have not done anything. Automatically you can see that there are few of the informations is highlighted. So quad ISP is enabled, Ethernet enabled, USB enabled, UART0 is enabled, right? So by default, the machine is understanding and then enabling particular peripheral. So for our application, what we required additional to these things is our UART1. So I'll just enable this UART1 and then I'll click on OK. So warnings can be neglected. So we have certain critical warnings. So for PSDDR memories, so we can neglect those portion. Okay, it is not mandatory that you have to debug the same. So after this, I'll just regenerate the layout. If you want, if you have messy block design finding, then you can have this regenerate layout option. You can click on that, and then we have validate. So this basically takes care of the error checking. If any of the pins are unconnected, which is floating, okay, which is not connected to any of the port, if it is made it as an external, then if it is not getting used, then it will show an error. So make sure that you have to make sure that there are no errors in your block design. So that is one aspect. So we have enabled UART1 here. Okay, just keep it in mind. Now you can see that UART1 is enabled. So I have set the baud rate as the default value, that is 115200. So that is a default baud rate. And then I'll just create a still wrapper. So first thing, created a project and then created a block design, added my block, and then I'm going to create a still wrapper for that. So it will take some time. So it will be done. wrapper is created. So it is getting updated. Our wrapper is there. Okay. So now we directly go to the generate bitstream. So it'll take time for one of the design. So to complete flow, and then later designs I'm going to take one more file, or we can rewrite this existing design as well. So we can add upon the peripherals along with the existing designs as well with respect to this. So now the intimation of the information of what stage your designs are, that will be showcasing on the right hand corner. You can see now it's running the design. So performing the synthesis first. So once after it performs the synthesis, like what it does after synthesis. So basically, after the synthesis, it is going to follow the three steps, okay, which is a part of your implementation. One is an optimization. The second one is placement, and the another one is a routing. So these three steps that will be followed in case of implementation. So after that, then we have a option of generating a bitstream, which basically converts your RTL code to the machine understandable code, which is either zeros or ones. Those data we are going to take, and then we are going to program the hardware. So without the bit file, we are nowhere going to design anything. So for any FPGA board, the bit file is mandatory. So what are the file structures in your Vitis flow is? So it is going to take .out or hex file. So that is in a embedded application environment, right? So we require .out file or hex file, so which can be programmed to the FPGA device. So it is taking time for the synthesis. Once synthesis is done, then it will go for the implementation. Initializing the design, maybe it is getting into the implementation portion now. I think it will start with an optimization of the design. So it is started with an optimization of the design. You can observe in the right hand side of the tool, top right corner. So I have the implemented design of the bitstream generation is successful. I'll just cancel it. So what is the next step is? So just I'll show you the design file. You can see here we have XPR, that is Xilinx project file we have. So we have the block and other things in these things. So now what I'll do is I'll just go to file, export hardware. So I'm going to export hardware. So I'm going to include the bitstream next, and then I'm going to convert into an XSA. Just you can observe here, we are exporting our hardware. So in order to create a platform, we required this XSA file. Okay, Xilinx shell archive, what I told initially. So it is going to create a archive file for us. So now what has happened just at the back end, you can see there is an archive file for us readily available for our design. So now what I'll do is here only, I'll just create one new folder for embedded application. Embedded application. Okay, so this is a empty folder. I'll just copy this path. Okay, now I'll move on to the next one more tool. So I am going to use Vitis Classic as of now. So this is one more tool which is required. That's why as a prerequisite I have told you what are the things are required. So one is Vivado. Vivado, the front end we have configured till XSA. Then taking that XSA file, we are going to build the application in embedded. So I'll just paste that path. Okay, first initially whenever we start up with a Vitis launcher, they will ask for a workspace where you have to create your project. Now you can see here in this embedded application, it is an empty now. As soon as I'll just assign the workspace, there are files are appearing there. You can see here there are metadata will be getting added where we'll have a checksum and other things. So I'll just continue with Vitis Classic. So this is how you see the Vitis IDE. Okay, so we have set the workspace first. Now what is the first step in our embedded application is creating a platform, right? So linking it from your XSA file. So that we have to do. So we have create platform project. So give the platform name. Okay, I'll just give it as UART. Okay, and then I'll browse for the XSA file which is there as part of the design. I've kept it here in design one. We have this is created now at 3:30 p.m. so that I'm taking that. Now what I am mentioning, right? So what this platform consists of, one thing is source file and header files, other things that I'll show you once the platform is created. The other part what I have shown you is that the cores. Okay, we have two cores. So we have PS7, Cortex A9, 0 and 1. So you can select, you have an option for the core selection here. Okay, which is basically a dual core processor we have. So either you can select whichever the core you are comfortable with. So it is not mandatory, but by default it will take any core. So you let it be in the same core. So I told you the other features so that you can run it on Linux or FreeRTOS also. But since we have Zing processing system, so let it be a standalone rather than a Linux or any other platform. So I'll just finish it. This will create the platform for us. So now the platform is getting created. So you can see here I was mentioning about support packages, right? So any application you take, so it will be taking the board support packages. Now coming to the structure of this, okay, what are there hardware wise? So we have XSA file, and this is UART XPEFM file. So we can open. It's going to be taking a character, your platform linking to your application, Okay, the name we have given project platform name, okay, for that. And apart from that, we have initialization of PS7 core. So basically this XSA consists of your bit file as well. Just you can observe in your this platform. So it will be taking your whatever the wrapper we have created. No, for that the bit file is generated. That will be available here. And we have initialization of core. Okay, so with header files, and there are set of opcodes for your design. So all these things are available here. Okay. So you can see what are the opcodes and what are the peripheral frequencies. All these things are available here. Okay. So then initialization of that. Okay. So just not look into the other things. So next I'll just show you what are the other parts. Now, since we have seen that initialization of PS7, right? So now we will see it in the PS7 standalone domain. So we have board support package, PS Cortex A9. We have include files. So what are the include files we have? So I'll just take a quick walkthrough with this xparameters.h. Okay, so I was mentioning, right? So one more aspect of your platform is that it will be storing the information of the frequencies or base addresses of particular peripheral. You can observe here. So PS7 DDR AXI base address is this. Okay, as I think Madam has explained you regarding a memory map, right? So all these things are available here. So whatever the peripheral we are having an access through this device, so we have DMA access, right? So DMA also there is a specific base address for that. And Ethernet, okay, dedicated to an Ethernet. Okay, whether you're taking it from processing system side, so we have the base address and then frequency of that and what rate it has to operate. So whether you want to make it for, I told try mode, right? You can see it here, 10 Mbps, 100 Mbps and 1000 Mbps. So it's basically differential signals. Okay, so you have to take it as a pair of the data. So like that. So this is for Ethernet. Okay, and this is for some peripherals with AFI. Okay, interface buses, you can use it there. And then we have bus configurations. There are like many bus configuration for Raspberry Pi also. There are buses and definitions you can give it with respect to the memory access. So all the informations you can find it here. So I'll just type GPIO. So GPIO also it is available. UART is also available. Okay, I2C I'll just type. I2C is not available here. So for CAN I'll just check. CAN is not there. Yeah, CAN is not there. So there are only few of the peripherals are given to the outside world that will be specified here. Okay, see, still there is another way around how you can access those parameters also. So you can define those memory address and then you can use it, and then you can find the resources as well. So standalone. So this is not relevant for your application. So then you have platform tickle files, whatever we have done here. Okay, so that will be taken care in tickle file. Whatever the actions we do in Vitis flow, so that will be documented in the tickle file of this. So I hope you got a clear picture about that. And then library sources as a brief insight to that. So what are the peripherals? So whether you wanted DDR memory with PS side, so you can access here. There are header files, source files for that. Okay, you can use that. Okay, so if you take that, what are the steps required? So you can refer to the documentation of this, or you can refer. I think there are no files here properly. It is built. So GPIO PS. Okay, so it is based on the version also. It is available also. You can see it here. GPIO dot GPIO XGPIO PS dot H GPIO. So what are the things you can find it here, whether you wanted a rising edge or falling edge with respect to an interrupt. Okay, that is also specified. So which bank you are using, okay, bank 0, bank 1, and then so base address. So it is basically defined as structure. Okay, so in structure you can see GPU configuration, whether initialize with ready signal handling, like you're going to have a status handler, a callback function, so platform data, so all the informations. So apart from this, there are dedicated functionals already available. So you can see here X, GPIO, PS, read. So if I'll go to this, there are three parameters here. So what it does, so if I'll just hold the control and then hover it, it will ask whether you want to go to that location. What that function does, that function definition is also been given already. So the what measures you have to take it. So everything is readily available for you in embedded applications. So you have to make sure that understand the particular peripheral, what you have to do it, whether you have to write. We have there are many things, right? Here, get direction, set output, enable any file structure with functionalities are given in your the source files of it is in the resources. So you had PS, USB, and XADC PS. All those header files are available. Now we have to wisely choose those header files. How do we add it in our project? So we are not going to add exceptionally, which is unknown, but it is known by the platform only. Okay, so all the files. So there are only few things we are enabled. So that's why it is not showing you all the peripherals here with the header file. So if you enable all the resources in your Vivado flow, okay, then obviously it will enable all the peripherals, and then it will give you corresponding header file and .c file for the usage. Okay, so I'll just what I'll do, I'll just close all these windows. Let me move on to the next step. Okay, so my platform is built and then ready to use it here, right? Okay, my platform is there. The next step is creating an application. So I'll just file new and application project. Next, I'll just click. Now you have seen that what platform name I have given is UART, right? So this is a platform name. So that is appearing here. Earlier it never used to appear here. Since we taken an XSA file and then created a platform, that platform, it is asking which if you are creating an application, it is asking for which platform you need to link it. Okay, so I'm linking it to the existing platform, that is UART. So you give the name of, okay, I'll just only give the print or print message. Okay, so some name I give, application name. So automatically you see that whatever the core we're taking from the processor, it is 0th core, right? So it is taken. I'll just click on next. Now it will ask for already there are certain examples available here. So let me not take any example. I'll just take empty application, finish it, so that you will get to know how later you can add upon those things. Okay. So I'll have the source file, which is having three things. So one is linker script, okay, which basically tells you information about what region you want to access, and then readme text. So this, if you have predefined example, they will come up with a readme file. Here you need to manually, you have to create a readme file for your application, and then selling specifications file. Okay. Now in this things, you are going to add a new file, create a new file. That is the next step. Okay. So what I have done, created a platform, created application. Now I am going to add a source file to this. So source file message print .c. So extension should be .c. So you can either select a C++ empty code as well or C code also. Since I have taken C code, so I am going to use this. Okay. Now I have to write some program. So instead what I'll do is I'll just take the program already given. So it's just a simple thing to make you to understand. So you can use a normal print statement as well. Apart from, we have here Xilinx printf as one of the header. I'll just hover this there, so you can see here what they have used it here. So we have character, 8-bit characters, each and everything it is taken. So we have the print. Either you can use Xilinx print, like printf, or print. You can use it. Okay, either of these two you can use it. So as of now, so it will gives you both the way flexibilities. Okay, so I'll just change the content. Good afternoon all. So I'll just use Excel, or I'll use print. I'll just see. I'll come to the session. I'll just put a semicolon. Okay, so I'll just save it. Now what I'll do is, the next, my application is there, so I need to make sure the designs are error free. So first what I'll do, I'll just right click on the platform. I'll build the project. Once after you have the ready designs available, then you have to build it. So basically we are performing a compilation of the code. Once the compilation is done, so if any errors or anything like that in the platform build, then it will showcase in build console window. So in the console window, in the bottom most part, you can find it. So it is almost done. So build is finished. So now we will go ahead with the building of this application project. Just rebuild it. Okay. So nothing to build here. Because already there is a build has happened. Okay. Now what I'll do, I'll just connect on hardware now. Okay. So I'll just turn on the camera for you to get to know. So I am using an hardware here, PingZ2 board. Okay, so I am going to connect the USB port, and already there are a jumper is given for that. So you can see here, so my device is turned on. Okay, now what I'll do is just go to this, and then I'm just going to program. Just before that, for a safer side, what we can do is, so we can have the one more terminal, so serial terminal, that is Terraterm. So as soon as I connected my hardware, so you can see there are serial terminal with COM port as detected. Okay, so COM4 is the port. I can click on OK, and then setup, go to the serial port, and then configure the baud rate. Okay, and then your settings. So keep this aside. Okay, so now you can observe this is empty, my Terraterm window. Okay, so now what I'll do, I'll just run as launch hardware. Okay. Can observe. So as soon as it is getting downloaded, so you have thing it has to come. The program is done, but why it is not displaying? It's no display. Just a minute. Okay, so I'll just add some other file. I'll just remove this. Just refresh. Nothing is happening. So I'll just remove it. I'll add the new file to our project. Our source. New file. Just take source file. I'll just take print image.c. Okay, so I have this in progress. So I'm going to build it. Yes, now it is taking. So earlier that underscore was not taken. Make sure that you give the underscore. So the Terraterm I'll just configure once again. Run as launch hardware. I'll just give relaunch. Yeah, you can see here. So hi, good afternoon, or welcome to the session. So that is come. So which is we didn't use any of the carriers written in our application, right? So you can use /n or /r along with that. So then obviously it will come in the new line with the first line as a carriage return. So we'll add that. So if you want, so just specify /n/r. So as that, and then I'll just rerun this so that you will get to know. So similar to this one, it will automatically takes the UART1 peripheral and then accesses it. Okay, then just have your settings. Now what I'll do, I'm going to build it. Sorry, run as and launch. Sorry, a build we have not done, right? So we have to do the build. As soon as you change the code in your C program, so you are supposed to do that building of the things. Then that is basically a compile option. And then finally we will run as launch hardware. Okay, so just program it. It will take time. So now you can see, so it is appearing in the next line. So the next command. So whatever you want to enter so that you can try it. Okay, that is one of the demos that what I just want to show you. The second demo, okay, as like let this be there, or what I'll do is I'll just remove this. Okay, I'll just delete this application. Okay, so it will be there in my project whenever it is required, so I can use it. If I'll enable this, automatically it will clears it from your application as well. Okay, so now we have only a platform. So the next portion of it. Okay, so the next portion for the demo. Okay, so I think we have covered with the first demo. The next demo is on the sending some byte of information through UART and then obtaining the data from the UART terminal. Okay, that is one thing. I hope the first demo is clear to you. Okay, anything you just wanted to add, let me know. Okay, no questions, I feel. Okay, so next we'll get into one more application development. So the same as a base, I'll just use it. New application project. Okay, and linking to the same platform. So whenever board is not required, you make sure that you turn off the board. Okay, so I'll just go to the next one. UART echo. Okay, so I'll not use underscores. You try to avoid underscore in your C files, otherwise it will not build it. Okay, so there are the length of the code, like name will be more, then sometimes it will cause us an error. Okay, so I'll just take, then I'll create the application for you. Let me take an empty application, finish it. Okay, so I'll just add my source code here. New file echo.c I'll give. Okay, just finish. So I have to write the code here. So please remember what are the things are required for you. Okay, for UART. Okay, so we have one is hash include double quotes. We require x parameters dot h. So where and which your address are specified. Hash include x UART ps dot h. Okay, so we required PSID UART file, those two things as a major headers. So if you want your C normal standard IOH other things, so if you want you can add those things. So apart from that, I'll just add one more thing. So Xilinx types dot h. Okay, so what these things consist, I'll just show you. X parameters are the base address. Coming to XUART-PS, the PSID UART header consisting of the header file of PS UART, entire thing, the structure of that. Okay, and then coming to the next one is Xilinx types. So which is unsigned type declaration of any variables like U32, U16, okay, unsigned 16-bit value or 32-bit value or 8-bit. Okay, so any user defined types, so you want to specify, you see here. So uint 8 underscore t will be defined as u8, u16, u32. So that if you use any of the unsigned declarations in your code, so that you can use this. So that is one thing. And as usual, the code, I'll just take it from the slide. Okay, so I'll just copy the header. I'm not copying it. So since I have declared it, okay, so you know why these are all things are covered. So now let me come to the code part. So I'll just explain briefly about this code, how exactly it will work. Okay, first and foremost thing. So in X parameters, we have the address, right? So we'll take the UART. Okay, UART base address first. So UART base address, you can see it here. Yeah, UART1 we are accessing, so we have the base address here. Okay, expand. Sorry, UART0. I think in our code, yes, 0. So UART0 we are using. So we are accessing that base address here, assigning to UART underscore base address, and then we have XUART PS. So whatever PS.h we have, no UART. So that will be having a structure of XUART PS. So I'll just go to the declaration. You see here, it's a structure. So configuration, input log, send buffer, or receive buffer, everything is there, linking to the platform, all the information. So first we will create a, I can say it's a creating an object or a driver file for the PS type UART. Then we'll take some variable int. So since we taken a int, so I'll just have a one more header. So we'll have standard io.h also if you want, you can add it. So next coming to the main program. So these three we have defined it to the global variables, and then in the local part we declared u32 UART data. So where this u32 is defined, which is in excel underscore types.h. So we make sure that when we use this u32, then this excel underscore types.h should be added to your code. And then we have configuration. We have taken one pointer. Okay, XUART ps underscore config. I'll just go to that. I'll just show you what is there. So this is linking to your the structure basically. Okay. So first we do the UART configuration, if assigning to a pointer. Now what we do is first we will assign configuration file linking to your base address. So that is where your UART configurations we are going to perform. For this pointer, we are going to assign the base address. Okay, we are configuring it. Now just checking the status. So status is now the nothing is there. So we are assigning the status value with configuration value of this. So what are the things it will take? It will take the object, UART object, and UART config file. What it will stores the base address of configured, like PS UART is configured with the base address. That value will be stored here, and then we'll have a base address directly. Okay. So if status is not equal to there are success things macros available. So I'll show you, which is available in status.h. So this by default, if it is a success, then 0 will be stored. So these are the status. This, if you want this also, you can add it in your code. xstatus.s. Okay. So you can add that. Otherwise also it will be part of the platform, automatically it will consider. If few of them headers, if you are not added, it might alert you or it will ask you to update it, so that you can do it. And then printf, if it is not equal to success, then you have to your should be initialized with failed data. Okay, so now while, so we have taken one variable, right, your data here. Okay, so in infinite loop, what we are doing, we are assigning your data. So we receive the byte. Receive in the sense you press some key in the with respect to the base address of the PS, then it will be assigned to a UART data. That UART data will be sent using UART XUART PS send byte. So this function will give you the whatever the data you are printing, that will be displayed on the terminal. Okay, that is what the major aspect. Just save it. Okay, so now what is the next step? So we'll build the project. So I'll just save it, Control S, I'll just build it. Okay, so build is finished. Okay, And now what are the thing is, I'll just turn on the board. I'll just access the, I'll just do the clear buffer. So I'm not doing one more time Teratom configuration since it is open. I'll just program this, run as launch hub. Just open the Teratom. So now nothing is displayed. I'll just going to add one more letter. Now I'm going to enter QWERTY. Q is pressed, so Q is displayed there. Okay, W is entered. So like that. So whatever it is there, no, I'm going to print it on my keyboard. That will appear in the terminal. Okay, so I'll just clear the buffer. I'll just type my name. Okay, that will appear. Space I have given. Okay, so I'll just type Coral, so that will appear. Okay, so once again I'll just clear buffer. So whatever I'll just enter, okay, chip in, so that will appear. Okay. I hope whatever the data we send it through keyboard, so that is displaying. So that is one more demonstration that what I wanted to show you. So you can try the multiple ways of playing it with any of the peripheral and then configuring the same. Okay, I hope this is clear. The coming to the next one, which is on demo 3. So we will access GPIO and then toggle PL side LED with delay. So that is the third demo, so that we will see. So basic idea is here. So we are going to blink LEDs so that it is visible to us and then we can observe the changes on the board. So that is the basic idea. And now what I'll do, so for the existing design, or I'll just create a new design. I'll take a design to the same project. I'll take zinc processing system. Okay, that's one thing. And now I'll add one more peripheral. Since I don't have any GPIO for zinc processing system, so what I'll do is I'll have one peripheral linking to this AXI GPIO voltage. So I'll just take this. I'll double click on GPIO. Now what I'll do is there are two demos that I want to show. So both the things we will configure. So one is buttons 4 bits. So this is PL side, what I'm doing it. We have LED 4 bits. So let us understand, if you don't want to do like this, okay, what you can do is, so I'll just make this to be external so that you'll understand. I'll make the GPIO, or what I'll do is I'll run connection automation and just type and just AXI automatic is going to take other blocks as well. So you can see here 2 GPIO which assigned with 4 bits. Okay, GPIO IO underscore 1 3 down to 0, and this is second GPIO, okay, which is taken for an LED, that is also 3 down to 0. So both the things I need to LED 4 bits and buttons 4 bits, right? So this internally what it is going to do is it is going to make sure that the already existing XTC files from the buttons 4 bits and LEDs 4 bit, it will be getting assigned to that. So I'll just run the block automation. So I'll just regenerate the layout. You can see it now, it is clear. Now regeneration part is proper. I'll just validate this design. Validation is successful. Now what I'll do, just create a wrapper for this. So wrapper is created. So what I'll do is, this is my top design earlier. Now I'll just change it to this design. So set as top, I'll just give, that will be reflected now. Okay. Now I'll just do the generate bitstream. So it is taking now the generate bitstream. Any questions? So it is taking synthesis. Now it is getting into synthesis portion. So what is the additional thing which in this block design is there is automatically the reset circuitry it is taken. So it is going to link to the AXI reset circuitry and then linking to your master AXI GP clock, right? So just taken the common clock, all the clocks are shorted and all the resets are shorted and then given to the reset unit. Usually when we operate any peripheral, it should be operating at half of the frequency of your processing system. So your reset PS is taken 50 megahertz. So your Zinc processing system is having 125 megahertz. Almost it will take 50 to 75 megahertz. So that's why the reset signal is 50 megahertz. So the reset circuitry will take 50 megahertz. So that internally it is going to take care. So either with respect to the block automation or connection automation, the tool will take care of that. So sometimes if you feel anywhere in the Vivado flow you're stuck, so this features of clock automation or connection automation or block automation, that will help you. So bitstream generation successful. So I'll just go to the project path. So we have just refresh. So now you see only one designs are there. Okay. So if I'll export this one, so what will happen? So the earlier the wrapper file will disappear. So what I'll do is I'll just make sure I'm going to export, then include bitstream. So I'm going to take the wrapper. So design to wrapper it is going to take. Then next finish. So for a safer side, what you can do is when you have multiple applications, so you create multiple projects for one each, so that it will be suggested. So have design to wrapper now. Okay. So what is the next step? So I'll just close this. Exit. Now I'll just take one more file folder, embedded system design to EST2. I'll just take EST2. Okay, so I'll just take this workspace, just open Vitesse. Need not to open multiple times, so you can have switch workspace option as well. So I am opening refresh like fresh the way how you can do it. Just give the different workspace. Just copy this. Launch LV. So the same steps that you need to follow. Create a platform project. So now I'll just working on GPIO. So I'll just take the platform as GPIO, which is PL side. Browse the XSA. Now design to wrapper. Finish it. So platform was done. Okay, I'll just create new application project. So I'll just link to the platform. So first we'll take LED blink. Okay, or blink LED. I'll just give LED blink only. I give. So I'll just take the empty application, finish it. So I'll add the source file to this. So I'll just give blink.c as the name. Finish. I'll just copy the code of this. There are two headers only I have added in this code. Just I'll show you. One is xparameters.h and another is xgpu.h. Okay, coming to the understanding of the code. So first we assigned a base address for this one, GPIO. Since we have two GPIOs here, so one is dip switch. There are 4 dip switches are here, so push buttons, not dip switch, push buttons, and then 4 LEDs are available. LED 4 bytes and this one. So we need to understand here. So you have two channels here, right? So one is channel 1 and then channel 2. So channel 2 is configured for LEDs in this sense, right? So you need to make sure that whenever you have an AXI GPU, so if you are using the multiple lines with single AXI GPIO, then you must have to understand it is linking with the channels. So according to that, so we have to align our code. So once the base address is specified from your xgpio.h, so this is basically your IO declarations. So entire thing, IO files are available here. First you can observe here. Okay, the structure with xgpio. So these parameters are linking to your base address of the peripherals used. Now we have driver we are creating is GPIO first, and then in the main program we initialize the GPIO by loading this structure, okay, referencing to that GPIO driver, and then base address we give. And once we initialize the peripheral, once after that, so we configure the direction of the peripheral. Okay, so GPIO underscore set data direction. So underscore. So when we go to this, I'll just go to this data direction. I'll just show you. Observe here. Here you can see your channels 1 or 2, right? So you are going to have channel. So which channel you are going to use it? Okay, GPIO instant pointer and direction mask. So I'll just go to the direction mask. So direction mask says if it is output, then 0 has to be given. If it is an input, 1 has to be given, right? So this you need to understand. So whenever we call any of the header files and that pertaining to that peripheral, so we have to go back and analyze that what are the structures of the peripheral we need to understand, then we have to work on the same. Okay, so set the direction linking to this object, and then we are selecting a second channel. So what second channel is, you can see here LEDs underscore 4 bits, 4 LEDs we have configured. That's why 0 have given 0x0 will be taking 4 bits of data, a nibble of information. So it will be set as output. Okay, that's why it is 0. If you want to set it as an input, then you have to give this as 1, and channel is 2, second channel we are selecting. So we have taken the while one loop, within the while one loop. So we have GPIO discrete write. So we have read option also. If it's GPIO discrete read, something is there. So that with read option, you can read the data from any of the push buttons. That also you can do it. That we will see it in the next demonstration. So we called some delay. This is a manual delay. So there is one more way of giving delay is we have sleep.h file, which is as a one more header. Okay, we add that and I'll just add and we'll see. Just go to this, you can observe. So the predefined microsecond, milliseconds delay that is available with this. So you can see here. So microsecond sleep, okay, you have or second, so only sleep you can find. So there are a set of codes for that. Okay, you can specify sleep of 2 seconds means 2 seconds it will work. So just we'll try with both the methods how it will work. So then we'll analyze that. Okay, so just have given some delay here. So let it happen. So now first what we are doing, so for LEDs we are writing it 1111 and then we are making calling some delay and then making all LEDs to go off and then calling some delay. So since the next while loop it will start from here. Now if we directly give 0, then it might not show you 0th instant, so it might directly go to the fth instance. So that means with high only. So in order to observe both zeros and ones on the LED on the board to blink, so I have given this. Let me build it. Okay, build the platform and project. That is the next step. Okay, I have the platform here. Just let me do the building of this platform. So in the console, you can find that if any errors are there, it will appear here. So you can debug those things. So build is finished. So let me build my project, application project. Build is finished. Now what is the next step? So we initialize with hardware. I'll just show the hardware. So I'll just turn on, you can observe now. So there is nothing is there now. So I have not programmed anything. So what I'll just do is I'll just program now. You can observe the hardware. You can observe now the LEDs are blinking, right? I hope my video is visible to you guys. So LEDs are blinking, right? So this is one way we can do it. So with this modification, so we shall test it with the sleep, but also we will try if possible. Just give sleep 2 seconds. The first and foremost thing, so after you change any code, so build it. And then you perform programming. It will stop now. So it will reprogram the device. Yes, it is happening. So 2 seconds of delay it is taking, and then blinking the LED. I think you can see it here. So either discrete way you can do it, or you can use the sleep command, sleep.h header. So 2 seconds it will turn on, 2 seconds it will go off. Okay, so now we have done for all the 4 LEDs, right? So we can try it for only specified. So let me give it as 1, okay, or 2. Second LED to turn on and off. Okay, so that we will see it. I'll just save it. I'll just blink, like I'll just build it. I'll just reprogram it. So while doing a reprogramming, it will erase us first, and then it will performs reprogram. Observe, only one LED is turned on now. The rest of the thing, the second LED, only it is turning on and turning off. So after 2 seconds of delay. So all these constructs you must be aware. So when you design anything in the embedded applications. So this is one of the example I've taken. So just let me turn off the board. Okay. So let us move on to the next one. So let this be there. Applications. I'll create one more application. So which is next to demonstration. The next one, and then final, I can say. So final demonstration that I am going to do it now. So with GPIs only, creating a new application linking to the same platform, and I'll just push button LED access. Okay, both push button and LED access. Next, I'll take the empty application. So why I'm taking empty application every time is so that you'll get to know the embedded constructs to be used in your designs. Okay, so it is easier for you when you start exploring some of the peripheral, how you can go ahead, okay, by referring the header files already existed. So I'll just take the new file. So push button LED turning on. Okay, LED on. I'll just take, let's see, we'll just finish it. Make sure in source code as you don't use an underscore, that it caused an error in the initial part. So sometimes the build will be failed. Okay, so now I have this thing. I have to add the source code for this. Okay, open this. So I'll just add the code from the presentation. So only 2 headers I'm using, X parameters and just gpio.h. So it left to you, okay, what type of headers you want to add for your application base. Okay, so let me explain you this particular code. So we have taken the same GPIO base address. So we have linked to only one GPIO and 2 channels we are accessing in our design. So one base address is sufficient for all the GPIO definitions. So we have GPIO driver, that is your objects we have created for the structure XGPIO, and then we have taken I think here I have not declared it here, right? So what I have to declare it for U32? So anybody, can you please mention what is the header? So either you can unmute or put it in the chat. What is the header is required for U32 definition? So there is no response. So what is the header we have to add? Okay, just let me tell any chat. No, I think. Okay, we'll address few of the questions later. They might be in the morning. Okay, so let me continue. So the header file, what is required for U32 is excel_types.h. Okay, that is one thing. So if you want, you can add it in your header file. Otherwise, also it will refers to the platform, and then it inherently it will take it. So first step as initialization will take, and then we set the direction of channels, channel 2 and channel 1. Now both are required, right? So one is push buttons access, another one is the LED blink, which is required, right? So both we are having. And in the while one loop, so we have push button declared, right, as a unsigned 32 bit. So that will be getting assigned with a discrete read it from the push buttons, which is channel 1. Okay, channel 1 we're setting it as an input. That's why this F is given. Okay, 4 push buttons are there. So whatever you do the actions on the push button, so that will reflect. So we have a discrete write, so that will be referring to the push button data, and then it will project it on the LEDs. That is channel 2. Okay, so this is a code we have. So build platform not necessary. I'll just save this, and then I'll just build a project. And finally, what we will do, I'll just program this. Yes, so the hardware is not turned on, so that's why the failure will come. Otherwise, it will be programmed. Now I have turned on. Maybe I'll just see. Yes, it is programming. Now, I think I'll just turn on my camera. Just to observe here now the LEDs, right? So whenever I press whichever the button, so the 4 buttons are there. So based on the push button value, then LEDs are turning on. Okay, you can see my video part. You can observe this. Okay, so these are the demos that I have to demonstrate for you. So you can explore more on the multiple aspects of the design with respect to embedded design portfolio. So I hope I have covered almost all. So thank you all. So with this, I think we are open for questions. I think Asha madam, are you there?
Yes, I'm there, Manjunath. Maybe they are
So,
tired from 2 o'clock. We didn't give them break. Continuously, we have taken.
okay,
So
okay, fine.
we are open to questions. You can ask questions.
Yeah, participants can unmute themselves and ask questions if you have any doubts for last session and previous session. You can ask your queries, or else you can type it in the chat box. We can take up the questions one by one. And in the meantime, also feedback form is shared by Asha ma'am. Request you to fill that feedback form also.
Asha madam, this feedback is separate for everyone, or we have to give it to
It
one
is
only?
a Google form. They can fill separate for each faculty.
There isn't selection for that?
I'm not sure. I'll just check and I'll let you know.
Okay. I think there is no separate feedback. I think it's only generic.
Hello, good evening, sir. This is Ilyas.
Yes.
Sir, could you clarify us the hackathon, live hackathon will be there, right? How it will be you will provide some problem statement for that we have to write code and like do like that or what? Like exactly how it
I
is?
think to answer your question, maybe Prakash will address you tomorrow, and even Chipin team will suggest you, and then they will have set up some guidelines. So you need to follow that. Okay.
Yes, yes. They will be advised tomorrow about hackathon, more on hackathon. And yeah, Chip and team also will get involved with this.
Yeah, it will be brief to all the participants by tomorrow, or maybe your point of contact. You have assigned point of contact, right? Everyone has assigned point of contact. You can contact them also.
Okay, sir. Okay, thank you.
So, like to address the gathering, so now any questions you have on the demonstration or applications we have shown you yesterday and today, if you required any clarifications, we are open for that.
Yeah. Yes. So, anybody has any question regarding that, they can ask.
So later onwards, you have to do independently, so you'll not get much of help from our end for that reason.
Hello.
Yes, Govardhan.
Yeah. Whichever the thing we did, we can do the same thing directly with Vivado, no? Why we need to use what we say embedded development for this?
See, we have two parts in this. Okay, when we have a processing system involved, then we must
Okay.
have to use the embedded platform. Okay, Vitesse is one of the embedded platform for that. So
But if we have pink board, in that we can directly use PL, no? No need of PS also.
yes,
Without using PS, we can
agree.
use PL.
Yes, yes,
PL
it
you
is
can.
up to you. You can use independently PL or independently PS, or you want to take up as an embedded system design, you can have both a combo of PS and PL.
Okay. Same reason we can do only with PL also, no? There is no if in
Exactly.
hackathon
Yeah,
also.
that is what I told you in the beginning. Independently, you can work with FPGA. Independently, you can work with microprocessor also.
Okay, okay.
So when adding upon to Madam's point, so when you have like requirement not sufficient with processing system, you can free to go to PL side. So you have to
Okay.
follow with the AXI interface.
Okay, okay. Thank you.
Yeah. Any other questions?
Hello, sir. One more thing.
Yes.
When we combine both and PL and PS, then we are using this Vitas, right? Vitas.
No. I'll just clarify this. Okay. So we have a processing system as a part of FPGA. Okay. So we have only few peripherals in PS. So let us take UART only, 2 UARTs only available. So if you want more than 2 UARTs, like UART 3 or UART 4, you want it. How do you access now in SOC? You cannot extend, right? So that is where the idea of this AXI interface has come into picture, where you can extend your peripherals in PL side. So that is where this AXI is required, mandatory that time. Otherwise, no need of this AXI. Directly you can implement any of the UART implementation independent to PS side or PL side, as mentioned by Asha Madam earlier. You got my point?
Yes, sir. Yes, sir. I got it.
Okay.
If there are no more questions, I think we can wind up, Prince.
Yes, ma'am. There are no more questions in the chat box. So I
Yes.
think participants have no more questions. and we can conclude this session. So thank you everyone. Thank you all participants for attending this session, and thank you Coral team for accepting our invitation. And thank you for delivering today's session. Am I audible?
No, your voice is breaking.
Okay. I was just thanking you. Thank you, Coral team, and thank you all participants for conducting such a wonderful session. Thank you, Manjuna sir, for conducting afternoon session. Thank you, Asha Patel ma'am, for conducting forenoon session. So now we are concluding this session. If participants you have still any doubt, you can type it in, on that WhatsApp group. Our team will take your concern. So thank you all. Have a nice evening. Thank you, ma'am.
Thank you,
Thank you,
Prince.
sir.
Bye. Take
Thank
care.
you, Prince and Chipin team.
Yeah.
And thank you, participants.
Thank you. Thank you all.
Thank you, Manjunath.
Thanks to you too, ma'am.